Nadine, are you ready to go?
Oh, hi. Can you hear me?
Yes.
Okay, yeah, I'm all set.
Perfect. So good morning, everybody. I'm Justine Sherry.
Hi, and I'm Nadine Jabbar, and we'll be co-hosting this session.
Yeah, so we're going to be talking about verification, broadly defined, and we have 5 really exciting talks lined up. Our first speaker is Jonathan Weiss. Jonathan is a graduate student at the Hebrew University of Jerusalem. And just FYI, he'll be looking for internships about 2 semesters from now. Jonathan, why don't you take it away?
Okay, thanks. So I'll be talking about proving server faults, RPCs for distributed systems in Byzantine networks, a joint work between Yossi, Albert, and I. Yossi is my mentor. So in this talk, I plan about explaining the issue of detecting a server that is not participating in our protocol, our solution, some evaluations, and future work. So traditionally, in distributed systems, nodes are expected to be honest and to trust each other. In this case, it's kind of straightforward how we would detect a faulty server. So let's run a quick example where a server sends another server a message, and after enough time that it didn't receive a response, it would report it. The other servers in the system would simply acknowledge that the other server is faulty and will attempt to deal with it by isolating it, removing it, or even replacing it. This scenario won't go as smoothly in a Byzantine environment where nodes can't trust each other because some of them might be malicious. So let's reinvestigate the same scenario. And once again, the server will send a message and await a response. And after enough time, it will report the other server. But this time, the other server states otherwise. And as a result, the nodes in the system don't or can't determine which one is the liar. So we are left with 2 servers pointing at each other and no actual proof about which one is faulty. A possible solution would be to simply remove both of them, and as a result, we would remove at least one malicious server. This approach has a few downsides because we are losing an honest node, which means we are losing processing power from our system, and we are making it easier for an attacker to cause denial of service on our servers, on a specific server, by simply accusing it. So the issue before was that in peer-to-peer communication, there's no proof for the victim that actually something went wrong. So our solution would be to introduce relays which would be witnesses to the actual communication between the 2 servers, and later on they will be able to attest against the malicious server. A naive solution would be to simply copy the message and send it through the relays to the recipient. Now when the recipient claims that it did send something, everyone knows that it's lying. Well, this works, but it doesn't actually scale well because we have a lot of bandwidth overhead when we need to copy a lot of messages, and this becomes a bigger issue when the system is big and the messages are big. We would actually want to shard the messages into small parts in order to send with each relay a small shard or a small shell of the whole message. But we can't really do that because we can't actually trust the relays to do that, to send a parcel or send a shell that they received, and even worse, they might actually alter that shell. To solve these issues, we are going to use error correction codes, which would add redundancies to our message and allow us to handle erasures in the system, which means we will be able to handle or withstand faulty relays which drop the parcel. In addition to that, we're going to sign the parcel in order to be able to detect that a parcel was later on, to detect later on that the parcel was actually altered. So let's illustrate it to gain better understanding. In our example, we're going to use error correction codes which can reconstruct the message with only 2/3 of the actual parcel. So to send the message, the server will simply encode the message into parcels, and then sign them and send each parcel to the relays. The relays will then pass the parcel on to the receiving server, and a malicious relay might drop or alter that parcel, but if it drops it, we can still recover. And if it altered the parcel, the signature will allow us to detect it, and the recipient will simply toss that altered parcel aside. So once the receiver receives enough parcels, it will verify the signatures, and then it will reconstruct the message. To respond, it will go through the same process in the other direction. There's a lot of overheads in our system, in this solution, which are introduced by the signatures we are doing. There's a lot of computational overhead because we are signing and verifying a lot of parcels and a lot of signatures, because the message now is sharded into a lot of parcels, or encoded into a lot of parcels, and that's a lot of signatures. And we are adding bandwidth to each parcel because we are adding a signature to each parcel. In addition to that, relays introduce additional network hops, which adds latency to our system, and again, more bandwidth because we are using error correction codes, which adds redundancies. So instead of that, we are going to use a direct call in the common case to enhance performance and latency by simply sending a message and expecting some signed response, which proves communication took place. Later on, we're going to take this signed response, and share it with the relays. In case the server doesn't give us this response or something goes wrong, we can simply revert back to using the relay method as I described earlier. To evaluate our system, we first implemented a small prototype in Go, which is based on gRPC and is actually an RPC library, which we call robust RPC, or RPC in short. We've run a few tests on AWS using up to 100 EC2 instances, and we've tested latency, bandwidth, and integration of our system into a specific distributed system. In addition to that, we've added latency between our nodes in order to model real communication. So in our test, there's the latency test. In the latency test, we've sent about 1 megabyte worth of data from a client to a server and inspected the time. So our RPC, as you can see here, has about double the latency of gRPC and the direct calls. In addition to that, we can see that it doesn't seem to affect, in this specific example, by the amount of recoverable loss, which is the redundancies in our system, in our test, and that adding more relays adds a little bit of latency. We can also see that direct calls is on par with gRPC, which means that in the common case, you should expect similar latency performance. To test the bandwidth, we've tested by how much our system inflates a single message of one megabyte again. And we can see that RPC has a super linear graph in regards to the recoverable loss. And in addition to that, the direct calls has better performance, but still not as good as gRPC. And that is because we are having to send more messages in order to share our proof with the relays. And lastly, the system that we tested with is a mixnet. A mixnet is a distributed system which attempts to hide from an adversary that can control some of the servers and be able to monitor the network, which user sent which message. Typically, these systems are expected to to behave to operate, in Byzantine environment. And as a result, we thought that it would be able to leverage RPC, and it's a good evaluation, we think. So in our test, we've tested a mixnet. We've built a mixnet with a stratified topology, which we can see in the top right corner, and with 3 mixing layers. We've sent 5 million messages through the mixnet and tested the latency of the whole system, which means that we've timed from the last message being sent into the mixnet and up to the last message being outputted by the mixnet. In our test, we can see that again we have similar results as the latency test, where direct calls and gRPC
2 minutes.
Are really close, and that the RPC has doubled the latency. For future work, we wanted to address a few issues such as RPC streams, which would enhance performance in our systems, and because currently we only have unary RPCs, we would want to handle because direct calls aren't always going to run between 2 servers. We are still having to face a lot of signatures by using an RPC call. We would want to avoid that by combining a lot of messages and parcels under one signature by adding some form of batch send into the system. And lastly, we would want to test RPC with automatically healing systems in order to see how it goes with actually recovering from faults. So the recap is RPC can detect non-participating servers in a system by using relays and error correction code. We've seen that direct calls can help in the common case to reduce the latency in the system and to have actually similar latency to standard RPC libraries. And lastly, we've seen that an RPC call doubles the latency compared to standard libraries like gRPC, but we still think it's a reasonable slowdown. Thank you.
Thank you so much. So if you want to verbally voice a question, go ahead and raise your hand on Zoom. If you want to type a question into the chat on Slack, Nadine and I are both watching that. So audience.
Okay, I believe Aaron had his hand raised.
Perfect.
So I'm going to unmute you. Please go ahead and ask your question. Okay. I can't seem to unmute him.
Aaron, did you have a question?
No, sorry, I was just clapping at the end of the talk. I didn't have a question.
Oh.
Okay. Well, I'll kick us off with a question. You showed a really nice example of using your library for mixnets. Do you have a broader set of applications that you're targeting with this? Like, can you talk more about other distributed applications that will benefit here?
I actually haven't thought about a lot of other distributed systems that would actually use it. We've discussed maybe distributed hash tables, but I think that any system that is synchronous might be able to detect faults and clear their system from malicious servers with RPC. But I haven't really thought about an actual distributed server, so I might need to get back to you with that.
Okay.
Yeah. But I'll get back to you with that.
Okay.
Or I'll write in the Slack chat later.
Okay. Well, I think we can take any further discussion into the chat on Slack. Thank you so much for your nice presentation. We'll move forward to the next talk.
Okay, thanks a lot.
Okay, so our next talk for today would be on incremental network configuration verification, and it will be given by Pengsheng. So Pengsheng is currently an associate professor at Zhangtang University, China, and his research interests include network verification as well as programmable networks. Please go ahead, Pengsheng.
Okay. Can everyone see the screen?
Yes.
Yeah, thanks for the introduction. I'm happy to introduce our work on incremental network configuration verification. Well, I would like to start this talk with the old famous saying that change is only constant in life, because we think it's quite the same for our networks. Operators in networks often need to make some changes in their configuration because they want to support new services, add new devices, or they want to enhance their security. And existing studies based on several production network and university networks already show that the update frequency for the configuration can be very high. But unfortunately, the change in configuration sometimes can be very risky. In some large production networks, a large fraction of the network incidences can be caused by configuration update error. And for this reason, nearly 90% of operators are not sure whether the configuration change they made will introduce some bugs in their networks. So how to ensure the network correctness when operators really need to make some changes in their network? The community of network verification actually proposed several useful tools that operators can use them to check the correctness of the configurations. So these tools can actually take a snapshot of the configuration files in the network devices, including OSPF, BGP, echoes, and they build a network model and check the properties like reachability, no loops, no black spots, isolation, and so on. So why these tools are not enough? Because we observe that the changes in configuration are often quite more. Returning to the previous three typical networks, we can see that for each change in configuration, they only modify a small number of lines in the configuration files and only touching a small number of devices. So in this setting, existing verification tools based on snapshot has serious limitations. For example, as we can see here, after we make some change in the configuration file, the snapshot only changed slightly, and large fraction of the network model is still the same and don't need to be changed. And equally, the properties will not be affected much. So large fraction of the state in previous verification process is still useful, but existing tools, they just cannot fully utilize them. So as a result, this can lead to unnecessarily long verification time. Even for the state of the art, they can take several minutes to verify a snapshot. So this motivates us to study the problem of incremental network configuration verification, or NCV. So NCV tries to leverage the state of previous verification process in order to speed up the verification, especially for the changes. So how to achieve NCV? Firstly, let's look at the existing configuration verifiers we already have. These verifiers can be broadly classified into two classes. For the first class, they analyze the they analyze the space of possible data plans. For example, here we can suppose this is the space for all the possible data plans. For example, some links may fail and we have a data plan. Another link may fail, we have another data plan. So existing analysis-based verification tools, they also model the space of properties satisfying data plans as a space. So in this case, we can see that the space of possible data plans actually fall in the space of property satisfying data plans. So this means that the property holds. But after the configuration change, some new data plans become feasible. So the space of all possible data plans can be expanded, and the previous result about the verification can need to be updated. So in order to make analyze-based verification tools incremental, we need to reason about how the change in the space of data plans will affect the satisfaction of properties. So this can be very hard, and honestly, we still have no clear answer to this question. And for another class of tools, what we call simulation-based verification tools, they simulate the data plan in order to generate the concrete data plan state. That is the FIB entries or forwarding rules. And based on the FIBs and the forwarding rules, these tools can apply the data plan verification algorithms in order to check the properties. So to make such kind of tools incremental, firstly, we need to reason about how the forwarding rules will be changed by the configuration update. And also, we need to reason about how the change in forwarding rules will affect the properties. So our first design choice is to use the simulation-based one, because we found that existing data plan verifiers like DirtNet and APKeep can already incrementally verify the changes in FIBs or forwarding rules. For each rule insertion and deletion, DirtNet and APKeep can even verify them in less than 1 millisecond, which is quite fast. So the remaining task is how to reason about forwarding rules changed. So this can be a slightly easier problem to solve. And we still have two options. Firstly, as used by the current version of Badfish, they use customized simulation algorithm to simulate the control plane semantics. But to incrementally generate the data plan state based on customized algorithms, we need to modify the customized simulation, which tend to be quite labor consuming. And as another option, we can also choose another class of tools which are based on general purpose tools like model checkers and the data log. So the challenge here is we need to ensure that the underlying tools should be incremental. So our second design choice is to choose the general purpose option, because we observe that recently we have differential data log or DDLog, which is a dialect of data log language, which can enable automatical incremental computation. So something change in the input, a data log program can automatically compute the change in the output, which is quite useful. So we model the control plane semantics using DDLog so that we can incrementally compute the FIBs differences. And based on the FIB differences, we can apply any data plan verifiers. But here we choose a modified version of APKeep, which can process a batch of rule updates. So please see more details in our paper. Putting all the design choices and enabling techniques together, we built RealConfig, which is a system to achieve NCV. And we use topology of fat tree to evaluate whether RealConfig can be faster in checking network configuration changes. So we consider several typical type of changes like link failures, a change of link cost or local preference. And for comparison, we consider the Badfish simulation, which simulates the control plane to generate the data plan state from scratch after the change. And also we consider RealConfig full, which stands for from scratch computation using real config after change. So this serves as a baseline. And we can see here, actually real config full version perform a little bit slower than Badfish because we, based on general purpose tools, less optimized. So it is a little bit slower. But for incrementally generating the data plan state using real config, after change of link failure or link cost or local preference, the time is much smaller. So we can see here, the speed up compared to the real config full version is actually 20 to 92 times, which is quite remarkable. Since the majority time to verify the changes in configuration is the time to generate data plan, this translates almost directly to the speed up in the verification time. So to conclude, we think NCV is a quite important and quite interesting direction because we observe that configuration changes are quite frequent, risky, and quite often quite small. And we show that NCV is feasible by building real config based on two incremental components. One is incremental data plan verification, and the other is incremental data plan generation. And NCV is beneficial because we show that real config can already speed up the verification of change by up to 90 times, even without too much optimization. And we believe that real config may be, it is not the best approach or the only approach to achieve NCV. And we are open to other approaches. And we are going to study more approaches to achieve NCV. And also for real config, we are going to apply some domain-specific optimizations and to make it faster. Okay, with this, I'm going to wrap up this talk, and thanks for the listening. I'm happy to take questions here. Thank you.
I awkward clap.
Am I over time?
No, you're right on time.
Okay, great.
Thank you, Pengcheng. So it seems like we have a question. No, we don't have any questions yet. Would anyone like to ask any question?
Looks like David Walker has his hand up.
Okay. Oh yeah, so David and Mina. Okay, I'll start with. Please go ahead, David.
Hi there. Oh, thank you. That was a wonderful talk, and it's a really great practical idea. I'm curious about the SMT-based verifiers that you looked at. You dismissed thinking about how to make some of those algorithms incremental. It seems like one route to doing so would be to try to identify the kinds of changes that are made frequently, and then to structure the SMT problem in phases. So there are these incremental like extensions to Z3 and such that might allow you to do that. And I'm just wondering if you thought it might be possible to characterize the kinds of changes that occur and hence be able to use some of that kind of incremental SMT technology to be able to speed up those kinds of verifiers, which have the advantage of being able to check properties for all inputs or for all unknowns of a certain kind. Thanks.
Very good question. Thank you. Thank you. Well, we also consider this option, that is to modify SMT solvers to be incremental. And we also talk with the developers of Z3. And our understanding is that SMT solver actually is to explore the solution space. So to make SMT-based solutions incremental, we need to make SMT solver incremental. So it needs to incrementally explore the solution space. when we add a new constraints into the SMT, so we will, it is possible to obtain some, incrementally obtain the results. Well, if we try to retract some constraints, some previously not possible solutions may become possible, but maybe we already throw it away. So in this sense, SMT solving maybe in some cases it can be incremental, but it's not it cannot be generally applied to any cases. But we are still open to the method to make SMT solver like this incremental. We are happy to discuss with people on this. Thank you very much for the question. Yeah.
Thank you.
Thank you. We'll take our next question from Mina.
Hi, thank you for the talk. It was very, very interesting. I was wondering, because sometimes, when there are, even small changes to a problem could actually change it kind of fundamentally so much that it takes much longer to solve. So I was just wondering, in the kind of the scenarios that you experimented with, did you ever kind of happen to observe some kind of changes that actually changed the solving time dramatically?
Yeah, thanks for the question. It's very, it's a very good question. Yeah. In our preliminary results, we actually consider very simple changes to the configuration, like link failures, which means that we bring down some interfaces of routers or switches, or we change the local preference or the link cost. But it's still quite simple. In the future, we'll try to test real config with real updates traces and see whether this is still the case, that real config can still achieve such remarkable speed up. But I think given the changes in the configuration file, is still a small fraction in most of the traces that we are aware. So we believe that the speed up can still be there, but I'm not sure whether it can be so large. But we will report the results to the community in the future if we have. Okay.
Thank you. Yeah, thanks.
Thank you. Next question from Anand, please.
Can you hear me? Yeah. Right. So I think for the dev workers question, I have a suggestion. I guess maybe you read so in Alibaba we published a paper named Jingjing last year CCOM. So in that paper we actually mentioned how can we propose an algorithm to calculate the incremental encoding from the SMT model and try to put the incremental formula put that formula in the SMT solver and to speed up the SMT solve. I think maybe you could read that paper and to see whether you can extract the algorithm to analyze the encoded SMT equation and to speed up the Minesweeper or some other related approaches. So that's the first thing I just want to mention. Yeah, I think that algorithm is just specific to the echo analysis. So I think if you want to move that algorithm to the configuration policy verification, maybe you need to put some efforts. But the second thing is about the evaluation. I guess comparing with Minesweeper may not be very fair because the Bytefish may not be very fair because
we're running short on time. Do you have a question or do you have comments that you want to discuss with the author later?
Oh, the second thing is the question.
Okay.
So my question is, did you compare with the Minesweeper because the Bytefish is not good at handling the link failure?
Yeah. Actually, we don't compare to Minesweeper because here we just compare the time to generate the data plan state. Well, Minesweeper doesn't generate the concrete data plan state, so we don't compare to Minesweeper.
I see. How many prefixes are in your evaluation?
Sorry, guys, we're running a bit long time.
Anyway, yeah.
Okay, we can talk offline.
There are more questions on Slack as well, so if you could please take that offline. Would that be okay?
Thank you, guys.
Thank you very much. Sorry.
Thank you so much. There's definitely a lot of interest in talking about this paper. So I hope to see the Slack channel beeping along in a couple of minutes.
Yes, it's already beeping actually.
Yeah. Thank you.
Yeah, thank you very much, Justin. Yeah.
So our next speaker is Noga Chutman, a PhD student at the Hebrew University in Jerusalem, who's advised by Michael Shapira. And her work focuses on the intersection of computer networks and machine learning with an emphasis on real-world deployability, which is the topic of this paper she's about to present. Noga?
So sorry, you guys, can you, oh gosh.
Oh, she doesn't look to be logged in?
Hello, can you hear me, guys?
Yes.
Oh gosh. Everything just, technical stuff. Hold on, let me just share the screen for a second. Okay. Sorry about that, you guys.
There we go. We can see your slides perfect.
Oh, great. Thank you. So hi, everyone. I'm Noga Chutman. I'm a PhD student at Hebrew, and today I'll be talking about online safety assurance for learning augmented systems. This is a joint work with my advisor, Michael Shapira, and our collaborator, Aviv Tamar from the Technion. So as we all know, machine learning and specifically deep learning is everywhere. In computer networks, we've seen a surge of works using DL to solve many problems such as video streaming, traffic management, caching, and many others. These ML-based algorithms do very well when the training environment is faithful to the operational environment. The problem is real-world networks may be very different from the training environment, leading to a drop in performance. The question then becomes, how can we reap the benefits of ML without paying the costs for bad generalization? We propose a general methodology for the safe deployment of DL-based systems. This is done by building into the system the ability to detect in real time when the system encounters scenarios it was not trained for. We call this the online safety assurance problem, or OSAP. Online safety assurance can help by facilitating switching to a reasonable non-DL policy when the system can't be trusted to make reliable decisions. Note that safety assurance is fundamental to computer and network system in general, as a default policy already exists, the algorithm being used today. Additionally, these systems need to operate in environments too diverse to be represented by their training data. To the best of our knowledge, this is the first attempt to tackle this issue. We now ground OSAP with some formal definitions describing the problem using sequential decision-making under a Markov decision process. So in a Markov decision process, an agent interacts with an environment. At time t, the agent observes the state of the environment st and calculates the next action at based on its policy pi. An action takes place, and this changes the environment, which leads to some unknown reward rt. The goal of the agent is to optimize the discounted expected return with respect to the agent's policy pi. Note that many algorithms employ a value function used to estimate the expected discounted return at state st. From an ML point of view, OSAP deals with a scenario that is largely unexplored in ML literature, which is what happens when a policy learned for one MDP is applied to another MDP. Why is this the case? Well, there are a couple of reasons. Training in a simulator or emulator, which is a standard practice, fails to capture real-world dynamics. Changing network conditions, for example, different cell towers, and of course, the introduction of new factors such as routing changes and network failures. Next, we present our proposed safety assurance schemes. So how do we measure the uncertainty of an agent? First, we look at the agent's input. If the input is different from the training environment, the agent wasn't trained on those conditions. Therefore, our first safety assurance scheme we propose is US, uncertainty with regards to the environment states. Note that here, deciding whether a test sample is too different from some training environment is a standard unsupervised ML task called novelty detection. Next, we'll look at the agent's output. Even if the input changes, perhaps the agent learns something useful to these current conditions. Here, we define two schemes, UPI for uncertainty with regards to the agent's policy, and UV for uncertainty with regard to the agent's value function. Unfortunately, there is no standard way to evaluate uncertainty with regard to the output. So we decided to compare the outputs of ensembles of either policies or value functions. So what exactly are we going to measure? US is evaluated through novelty detection. Here we had a couple of options. We chose a classic method called one class SVM. For UPI, we use an agent ensemble. This scheme captures the idea that if each agent is certain of its own individual policy, it is expected that their output, which is a probability vector, would be similar to one another. So here we calculate similarity using the callback-Leibler divergence, which is a commonly used method for this task. For UV, we use a value function ensemble. The intuition here is that if there are multiple but different policies pi, different agent actions might differ as they follow different policies, but the values they calculate would still be similar. The output of a value function is a single value. So we evaluate this similarity through the sum of distances between the values and their average. Note that both UPi and UV output a continuous value. So we need to set a bar above which a sample is deemed dissimilar. Now that we know how to measure uncertainty, we ask when should the system switch to its default policy? So in order to avoid switching prematurely, we consider a sequence of key data points, and we default only if the uncertainty is detected n consecutive times. Therefore, setting the threshold involves configuring at k, m, and also for UPi and UV, the bar above which an action or value are considered uncertain. Note that there is an inherent tension between optimizing the performance when the training and test environments are similar and controlling the possible damage when this is not so. Therefore, we need to think about this a little bit differently. So the thing is that our thresholding methodology used in this paper is basically just to allow us to do a safe comparison. But this thresholding methodology is obviously open to changes, and you can use it to reflect riskier or safer choices. We now turn to evaluate our three safety assurance schemes in action using adaptive bitrate or ABR in video streaming. So when streaming a video, a client interacts with a video server. Each video is split into chunks. Each chunk is stored in different bit rates corresponding to the quality of the chunk. Because each chunk is stored at different bit rates, the client needs to request the next chunk at a specific bitrate R. The server then returns a chunk at the requested bitrate, and the client can continue watching. The ABR algorithm is responsible for deciding which is the best bitrate. If the algorithm undershoots, the client will suffer from bad resolution. On the other hand, if it chooses a bitrate which is too high, the client will have to wait for the next chunk to be delivered, a situation we call rebuffering. So to evaluate OSAP, we use a DL-based ABR algorithm called Pensieve as our learned policy. We implemented our three safety assurance schemes as variants of Pensieve. And as the default policy, we chose a simple yet effective ABR strategy called buffer-based, or BB. Finally, we evaluated our implementation using both synthetic and real-world data sets. So let's get into some results. This figure depicts the results for each of all considered ABR algorithms when the training and testing distributions are the same, what we call in distribution. Those algorithms are default BB in red, vanilla Pensieve in blue, and the three safety assurance variants, which we call A ensemble, ND, and V ensemble. The y-axis is the average reward, while the x-axis shows the different test datasets. The first two on the left, Belgium and Norway, are real-world datasets, while the rest are synthetic. So how do we allow for a fair comparison? Here we calibrate A ensemble and V ensemble to measure performance of ND. When looking at the figure, we can see that Pensieve, again in blue, outperforms BB in red across all distributions. So using Pensieve in distribution makes a lot of sense. Note that our three safety assurance schemes perform better than BB, but not as good as Pensieve. This is a necessary cost in order to perform better when the training and test distribution differs, as we'll see in the next slide. We now examine the results of the same algorithms when the training distribution is different from the test distribution, a situation we refer to as out of distribution or OOD. Here, we depict the performance of the agent trained on the synthetic gamma dataset on the left and real-world Belgium on the right. Again, the y-axis is the average reward, and the x-axis lists the test datasets. The results of an algorithm which selects the bit rates randomly is shown in pink. It's clear to see that the blue bars showing the performance of pensive are lower than BB, marked in red, almost all the time. Note that even in some cases, pensive performs worse than random. Finally, we contrast the 3 safety assurance schemes when out of distribution. Here, the x-axis shows the maximal, minimal, mean, and median values. We normalize the results so that the performance of 0 corresponds to random's performance, and 1 with BB's performance. We can see that all 3 safety assurance schemes are better than vanilla pensive in blue in terms of minimum, mean, and median values. ND in light green is a safer choice. The minimum is lower, while the mean and median are higher. This is because this scheme leads to v-faulting if the agent was not trained on the input. V-ensemble in light blue can get a very high maximum value, while improving upon pensive in terms of minimum value. This is because this scheme utilizes the knowledge gained during training when testing out of distribution. Remember, the threshold is flexible, so it can be chosen to obtain safer or riskier results. Interestingly, A-ensemble is essentially dominated by the other 2 safety assurance schemes. Note the significantly lower minimal value and worse than random mean value. We conjecture that this is because each agent might learn a different good policy, causing the high variability between agent outputs, even on the training data itself. So to conclude, we propose detecting in real time when the decision reached by systems are no longer valid and defaulting to a safer alternative. Initial investigation shows that incorporating online safety assurance into ML-driven systems maintains good performance when in distribution, while also being safe out of distribution. Lastly, we have some exciting new ideas for future research, so stay tuned. And I think that's about all the time I have for today. So thank you very much for tuning in, and please feel free to review the full text for more details.
Thank you so much.
Oh, thank you.
So as before, oh, we've already got a hand up. All right, Akshay, go ahead.
Hello. Hi. Yeah. So I thought it was a really nice talk and good work. I guess I have a question as to like what the limits of this the thresholding approach are. So like if I have input variance and then suddenly my MDT makes like a really bad decision. Like I'm thinking of like cluster scheduling or something where I schedule like the completely wrong job onto the wrong node. And then like my job completion times, just because of this one decision, are messed up for the next n iterations. Is there a way that we can possibly hope to deal with this situation, or should we just give up and like try to revert to like your idea of a safe algorithm after we've made this bad decision once?
So actually, that's a really interesting question. Thank you for that. I think that I don't believe in giving up ever. Thing that pops into my head as you were talking is perhaps we should check, I mean, you were talking about thresholding, but maybe in systems like clustering, which you have more data, more specific domain data, you can add some sort of reflector or something to some data from the actual system that would tell you, okay, this is really, really wrong. So I don't believe in like throwing out all the heuristics and smart things that we have learned about all those amazing domains in the future. I think we should think about incorporating those into the system. So here, for example, for video streaming, we just, in this particular example, we just look, at the data we have, but we could also incorporate other metadata and then, extrapolate from there. I think that could be a good solution. Does that make sense?
Well, it made sense to me. Next question is from Alexander Diesmuller.
Yes, hello. First of all, great topic and really exciting work. And I was just curious about this trade-off before picking the thresholds. I mean, as you mentioned, there's somewhat of kind of a decision on how we do. But just my question is a bit in a practical sense. How would I start? Like, I mean, and to start with, I have to pick a threshold. So, are there any kind of is there any kind of reasoning I can use to kind of pick some initial threshold, or like, do you know anything about kind of like the range of values I can pick, or like what is this space I have to pick the threshold from?
Well, thank you for that question. It's a really good point. I think that this is actually something that we want to look at in future work, because I think every domain, obviously every problem is going to have their own methodology to it, but maybe we can find something that is more general to give like just, initial guidelines to work with. I'm afraid I don't have anything written down on that yet, but it's definitely going into future work. How to do it specifically, I can't tell you right now, but there are several options that you can try. I think that with every system, you have to bootstrap at some point. So just trying out like the data from your last couple of days and then try to incorporate that would be a good start, I think, and then build from there. But I'm hoping that perhaps in the future, I'll have some more intelligent thing to say about that.
Thanks a lot.
Thank you so much. I think we'll put any further discussion into the Slack, and we will move on to the next talk.
Thank you.
Thank you. So our next talk will be on towards verified self-driving infrastructure, and it'll actually be presented by two people, which are Ali and Bengzhou. So they're both PhD candidates at University of Urbana-Illinois-Champaign. And if anyone is interested more in their talk and has potential internship opportunities that align with it, please feel free to contact them. I'll leave you guys to it. Good luck. Sorry, but we can't hear you if anyone's saying anything.
Oh, sorry. Just start from beginning. Thanks for the introduction. So let's start with answering the question, what is self-driving infrastructure? It consists of automatic controller that drive the infrastructure. And this picture shows the workflow of a controller. The controller sends the system by passively receiving events or actually collecting metrics. It then controls the system to achieve high-level policies. This form a closed-loop control. So this controller makes closed-loop dynamic decision to achieve a high-level goal across one more layer. An example of high-level goal can be to achieve 100% utilization of the physical network capacities. So such self-driving infrastructure is deployed in a range of environments, from small enterprise private infrastructure to large public cloud providers. So here are some examples of SDI elements. The service layer contains service mesh system like ECU linker. It consists of controller like layer 7 load balancers, circuit breakers that control the traffic in and out to services. The virtualization layer contains orchestration system like Kubernetes and SX that consists of controllers like schedulers, autoscalers that control the lifetime of VMs and containers. The network layer contains self-driving network like SDN that consists of controller like traffic engineering, routing that control the underlying networks. So what are the potential problems with SDI? Well, the overall system of multiple controllers can become very complex. So this picture illustrates such complexities. The controller in the orange box on the left are interacting with each other and also with the environmental events in the green box on the right. They interact by manipulating the system metrics in the middle. Such complexity can result in failures from performance degradation to service outage that are hard to predict before deployment. So let's look into one particular example that demonstrates how such complexity can cause a performance oscillation. So there are two applications deployed in a data center network. Each has two replicas and one load balancer that distributes requests according to average response time. This shows routing paths by the ECMP hashing for the green application. And now more requests are sent to the replica 1. Similarly, this is the path choice and request distribution for the yellow app. So everything is stable initially. And then there's a surge of external traffic on this purple edge that causes the yellow replica 1 to see a larger response time. This caused some of the yellow traffic to be shifted to replica 2. And then this results in delays on this red edge, causing the green load balancer to react and redistribute some of its traffic back to the replica 2. Because now more requests are being processed on this red node, It results in delays for replica 2 of the yellow app. Then the yellow load balancer in turn shifts some of its traffic back to replica 1. Now, since the red edge here carrying less traffic, the green load balancer may decide to shift some of the traffic back to replica 1. And there are still external traffic on this purple edge. The yellow load balancer may react again, and so on and so forth, that cause an oscillation. Note here that such oscillation only manifests under certain combination of non-deterministic interaction between load balancers and ECMP routing choices, which make it difficult to predict and to diagnose in pre-deployment stage. So with observation of the potential problem and also the increasing complexity of the SDI, in this work, we aim to call attention for the need for formal understanding of the self-driving infrastructure. So first, we identify 4 key characteristics that distinguish the space. And second, we study real-world problems. And third, we propose a proof of concept verification approach. So let's talk about each of them. So we first identify 4 key characteristics that complicate the SDI. First, it contains dynamic controller that run as a continuous control loop. So in the oscillation example, the layer 7 load balancers are the dynamic controllers. Second, the interactions are non-trivial, vary between goals or shared dependencies, and possibly with some non-deterministics. And third, the controllers are manipulating quantitative metrics like end-to-end latencies or load, rather than binary properties like network reachabilities. Fourth, the system is cross-layer. In the oscillation example, the components are either in network layers or service layer that fail to have a cross-layer knowledge. So here have those key characteristics been handled in previous work? So here we're looking into one of the most closely related work, the network configuration verification, like Minesweeper, Planktons, and see if their techniques can deal with the key characteristics. So they do have dynamic controls, but they're limited to specific routing protocols like BGP, and they only focus on reaching a convert state rather than continuous closed-loop controls. And they do deal with non-trivial interactions, but they're limited to a narrow type of interaction that basically dealing with IP address and via routing advertisement or echo. So none of them can include the quantitative metrics and cross layers. So we can conclude here that those key characteristics pose new challenge for verification. And next, we study if those key characteristics manifest in real-world problems. We look into incident reports from public cloud providers and issues in Kubernetes issue trackers, and also we further demonstrate a couple of additional problems. So due to time limit, I will be only looking into incident reports and also one of the potential problems. So in the incident report study, we look into 53 public reports from Google and Amazon that have enough documented details. And we examine if the key characteristics play roles in causing, propagating, or complicating each incident. So this chart shows the study result, where each characteristic play roles in some amount of real-world incidents. So we demonstrate here that the key characteristics that we identified do manifest in real-world incidents. So what else can go wrong? This is one of the potential problems we describe in the paper. Such oscillation problem is caused by the interaction between the scheduler and deployment controller and their conflict configurations. We reproduce such an example in a real Kubernetes deployment, and this figure shows oscillation of the pod placement that is resulted from the bad interactions. So I will now talk about details, and please check out our papers. So the interesting thing is that in the paper, we describe this as a potential problem, but we actually later see similar problem occurs in the real world. And these are the screenshots for the report by actual users. So just summary from our study, the 4 key characteristics do manifest in real world incidents, and the comprehensive verification should model all the 4 characteristics. With this, I will hand over to Ali to talk about our verification systems.
Thank you, Binjay. Can you hear me?
Oh, yeah, we can hear you. Please go ahead.
Okay. In order to alleviate the problems that mentioned so far, we propose a proof of concept approach in which we treat the abstract models of our control components as well as the environment as parametric transition systems and use symbolic model checking in order to check for safety and liveness properties about the system, which is usually encoded in temporal logic such as LTL. In case the model checker finds a violation, it reports a counterexample, including the values for the parameters as well as the execution steps that can lead to the violation. We can also use the system to synthesize safe parameters that make sure the property never fails. In our work, we use new XMV, which is a state-of-the-art symbolic model checker with nice features such as support for integer and real value parameters that can be used to model quantitative metrics such as real-time load and latency. I should emphasize that the goal of this work is not to provide a new verification tool, rather it is to see how far we can go with an off-the-shelf tool. Specifically, we are interested in evaluating the effectiveness and the efficiency of the approach. For effectiveness, we use two case studies. In the first case study, which is inspired by a real-world incident reported by Google, we have a service running on infrastructure consisting of a set of nodes and a service frontend that distributes the incoming traffic among the service nodes. We update an update rollout controller that brings some of the service nodes down, updates them, and brings them back up again in a non-deterministic order. And up to P nodes can be updated in parallel. We also model up to K non-deterministic link failures. And let's say the operator is interested in knowing that at any time, at least M service nodes are available, meaning they are up and reachable from the front end. Depending on the topology and the values of the parameters, this property may hold or fail. Say in this example, we want to see if the property holds given the topology and the parameters shown in the slide. We model this and ask the model checker if the property holds. NewXLV provides the following counter example. First, two link failures partition the front end from B and C and D, bringing the number of available nodes to 1. Then the update rollout brings E down, bringing available nodes to 0, which is less than what we wanted, and so the property gets violated. This was an example of verification. We can also use the system for parameter synthesis. Say in this topology, we know that we will have at most one link failure, and we want to make sure at least one node is available. We want to know what are the safe values for the number of parallel updates that make sure the property holds. In this case, the model checker would synthesize values 1 and 2. The first case study was about the safety property that says something bad will never happen. In the second case study, we study a liveness property that says something good will eventually happen. And for that, we use the load balancer and ECMP example that you saw before. We model this, and I'm going to skip the details of our modeling, for which you can refer to the paper, and ask the model checker whether the system eventually stabilizes or not. The model checker produced a counterexample, including the execution steps, as well as the values for parameters such as the input traffic and the relationship between load and latency per each device that lead the load balancer to oscillate permanently. Now we shift to the efficiency experiments. For that, we repeat the experiments in the first case study with various fat tree topologies of various sizes, an example of which you can see in the slide. And you can see the results here. Generally, runtime increases exponentially with the size of the input. Still, we think it's not bad. For example, for a factory with about 100 links, 50 nodes, and 2 link failures, verification finished within 3 minutes, which is promising given the fact that we deliberately omitted any domain-specific optimizations here, even though we had the chance to do so. So for our future work, we think we can improve the scalability by domain-specific optimizations inspired by the network verification works. And I should also mention that the biggest challenge of our work is modeling the infrastructure and control components. Still, we think there is hope. Some standards are emerging, systems like Kubernetes or IOC platforms like Terraform. Also, in our experience, the high-level control logic of these control components is much simpler than their low-level implementation. So there is hope. To conclude, we think that self-driving infrastructure is an interesting emerging space that needs formal understanding. In this paper, we took the first few steps and got interesting results, but we think much more can be done. Thank you very much.
Thank you for your talk. It was very interesting. I'm going to start with the questions from here. Mina, please go ahead.
Oh, I was actually clapping, but I also had a question, so I can just go ahead and ask. Right. So this is very cool. I was just wondering, you mentioned one of the problems, like the challenges, is with quantitative measures like latency and throughput. I was wondering if you had like any case studies or have looked into any case studies and about that, and if you have, what your experience was with those.
I can, yeah. Thanks. Yeah, I can answer this question. Yeah. So actually, our second case study, the liveness property with the load balancer, is exactly about some quantitative metrics such as input load and some, for example, the weight of the load balancer, which are actually real values. Also, the relationship, the real linear relationship between load and latency per each device. All of these are actually real valued parameters. Which we actually encoded. And as I said, NewXMV has this nice support for infinite domains. By infinite domain, I mean support for values such as integers and real valued parameters. And as you can see, we could analyze this case and actually got it produced a counterexample for us in this case.
Right. So I just to follow up on that, were you asking questions about what the latency is going to be? But so the questions about will the system eventually stabilize? So the latency and those measures were used to kind of model how the system is working.
So yes, exactly. So the latency is how. So the load balancers in our model are actually sensitive to latency, and they shift the traffic based on the latency that this backends experience.
I see. Great, thanks.
Yeah.
Okay, we'll take our next question from Inan. Please go ahead.
Oh yes, so interesting work. Well, my question is, why this is specific to the self-driving network? I mean, I think, for example, the liveness property verification, might be general enough for every network. Why this is specific to the self-driving network? This is my question.
I mean, I can also answer this one. Please feel free to add anything at the end if you want. So yeah, that's a good point. It's not as specific to self-driving infrastructure, and actually there were some works, I think last NSTI, that were actually checking liveness properties for network layer specifically. But our point is that, okay, we need to probably go even further than that, because of all these other layers in your network that still can cause problems, but nobody in the network verification community, at least, is paying attention to those parts. So your point is valid, but we think we should go further than that.
Okay, I think we can take one more question. I think Akil had his hand raised first, so I'm going to let him go ahead.
Hi, this is Qiao. Thanks for the talk. Very interesting. So I guess my question would be, in the early part of the talk, you mentioned that one key limitation is of Minesweeper and all those tools is they only verify a stable state. And it looks like in this particular example, you are also verifying, okay, in this case, you are verifying will the system eventually stabilize. But in your case one, you mentioned that, okay, you really are interested in verifying a stable state when network finished computer route. So I guess my question is, in your current design, are you able to verify routing convergence or not?
Okay, because again, this is about the second part. Okay, maybe Bingjay, do you want to take a stab at this one?
You can go ahead and answer it, yeah.
Okay. Okay. I can also answer this one. So the point, so the answer is that yes, we can also verify whether the system converges or not. Also about the point about our first case study, which was about a safety property. No, it wasn't actually for a converged state. It was actually, so there are multiple control components in that example, like 3 control components, like one is the update rollout, one is the actual network who's doing this route tree computation every time the topology changes, and one is the environment. And here actually, okay, we specifically say that we want to check the property each time the network is converged. But actually, the whole infrastructure is not necessarily converged. There are still updates like going on. Maybe still the environment can send more like link failures. So in that specific counter example that was actually mentioned, actually that property violation happens somewhere in the middle of the computation of the whole infrastructure. So it's not a converged state of the infrastructure. It is a converged state for the network reachability computation, but it's not converged for the whole network. So again, you can even like check for these violations during these transient states as well. We don't just focus on the like just converged states.
Okay, yeah.
Okay, great.
Thank you very much. Sorry, we're out on time for taking any more questions. Please use the Slack session, and Sherry will introduce, Justine will introduce the last talk for today. Thank you.
Yes, so our final speaker is Tim Nelson, who's on the faculty at Brown University and is interested in the intersection of networking and formal methods. He's going to talk to us about solver-aided multi-party configuration. Tim, are you ready?
I think so. Can you see my slides?
Absolutely. Take it away.
All right, so like the slide says, I'm Tim Nelson, and this is joint work. So let's say we have to configure a system. Well, it might be a network. It might be something like a Kubernetes microservice architecture. There are a ton of tools out there that help you configure networks via synthesis. I cite NetComplete here because it's my favorite, but there are a ton of others. And the workflow that they espouse, the worldview, sort of says, well, there's a space of configuration settings, and we're going to try to synthesize some values that go into those settings. And implicit in this perspective is the idea that there is one sort of monolithic team, one set of goals, one set of people who are going to be deploying this configuration. And in reality, that's not always the case. Sometimes there are multiple teams, multiple business units that may even have different perspectives on the operation of the system. So let's say we have one team, they're configuring a Kubernetes service mesh, and another one that's configuring Istio atop that. Well, those are different teams. They have different perspectives on the system. They may have overlapping settings that can influence the system similarly, but even their configuration languages aren't necessarily the same. So what does this look like at the solver level? Well, to take the NetComplete perspective, right, we could have all of the teams, all the administrators supply their sets of goals and maybe some partial configuration to the solver. If the solver succeeds, great. It's going to provide a full configuration, which can be partitioned up and deployed piecewise. But what happens if it fails? Well, if it fails, now a bunch of disparate entities, different people, different teams, have to negotiate over how to resolve this goal conflict. And this is what this work is about. So you might think, and certainly I thought at the beginning of this project, that, we're using solvers, so maybe we're going to get a core back, and that's going to tell us which goals are in conflict, and we go from there. But it's actually not quite so easy for a couple of reasons. First, you might have business or regulatory constraints preventing you from sharing your full configuration settings with your counterparts. And furthermore, just because you want to negotiate with somebody doesn't mean you want to supply them with an exhaustive description of how exactly you're doing what you're doing. You want to figure out what needs to change and change it. And finally, maybe more subtly, right, giving you a set of goals, my goals, doesn't really help you understand how your configuration needs to change in order to help me realize those goals, right? This is especially true in a NetComplete setting where you and I have some fixed configuration elements that we're synthesizing with respect to, okay? So concretely, what does this look like? Well, let's say the Istio admin has a couple of services and they want to provide access to those services on some source and destination ports. Well, maybe the Kubernetes administrator would take a step back then and ask, okay, like I think I understand what you want, but how can I give you that, right? So our idea in this work is not just to supply goals in the case of failure, but to supply what we call envelopes, right, in the sense of a safety envelope for an aircraft. What can you do in your configuration that will give me what I want, right? So rather than just providing the goal, we're going to say, in this case, something very simple because it's just on a slide. You could help me by not blocking that port, please. Okay. So for those of you in Team Logic in the audience, you'll recognize this as a sort of variation on abductive reasoning, right? We have some initial configuration settings. That's our environment we have to work with respect to. And we want to synthesize a formula, not a configuration. We want to synthesize a statement about what B's got to do in order to satisfy A's goals. And crucially, the key here is that B, this formula over B's configuration, really is in terms of only what B can control, the knobs and dials in B's configuration, not anything about what A can do, or perhaps any of the other administrators. So there's a bunch of ways that we might imagine going about synthesizing this constraint on B's configuration. What we're currently doing is we start with A's goals, we expand those goals into logic formulas in terms of this unified model of the system that cross-cuts both of these interests. And then we substitute A's current configuration settings in, and then we do simplification that produces a formula entirely in terms of B. Now, again, there's a bunch of other ways to do this. In particular, there's some work at Ishkar this past year on using, for instance, syntax-guided synthesis to solve this problem. So there's a bunch of technical ways that we might go about this, but the goal is to provide suggestions that focus negotiation. Rather than just saying what I want, we're going to tell you what you can do to give me that. Okay, and it turns out, by the way, that this isn't really one monolithic problem that we're trying to solve. It turns out there are different organizational contexts. If I, Tim Nelson, am trying to negotiate with Amazon Web Services, well, if they say, no, sorry, Tim, we're not going to do this for you, I'm sort of out of luck. I'd better go and change my goals. But in contrast, let's say that I'm talking to the system administrators at Brown University. Well, if I want something that they can't give me, I can go upstairs, or nowadays, of course, give them a call, and we can figure out how to reach an agreement so that I still get what I need and they get what they need as well, with a little bit of give and take. So again, organizational context really turns out to matter. And in our prototype, we embrace that. So we've built a tool called Muppet, which accepts configuration targets in very limited subsets of Kubernetes and Istio configurations. It attempts synthesis via a solver. And then should that synthesis fail, it will generate envelopes and facilitate a negotiation. Now, there's a lot of specifics about how that workflow happens. I'm going to direct you to the paper in the interest of time, because I want to be able to talk in a little bit more depth about some of the research challenges that came up here. I think maybe the most interesting research challenge to me is that these envelopes are not English sentences. They are logic formulas. And we have to figure out how to present those in a comprehensible way to the users, right? It's just a formula. It's not yet truly an explanation in natural language. Another point is that these formulas are very often disjunctive. There are multiple ways that you can go about satisfying an administrator's goals. This is key, actually a strength, right? Because if you're given a set of options, it's that much easier to satisfy the goals of administrator A. But the trouble is now there's this question of how do you present a set of options when that set of options comes in logicful format. Also, one might be very curious, well, why does this envelope actually get me what I want? Can you give me traceability and responsibility for these settings? The most important problem that we're having is the fact that it's actually kind of tough to get concrete configurations. And here's why. So when I started this project in the early summer, I thought this was just going to be an application of synthesis technology to the microservices domain, right? Kevin and Andrew came on board and we started working. And when we began to talk to practitioners, we kept being directed to these conflicts that were happening. And the practitioners we spoke to kept pointing out conflicts that were happening across the provider-customer boundary, which meant that it was very difficult to get us concrete configurations, right? So I want to end my talk with, I think, enough time for discussion, but also a call to arms. If you're experiencing or have experienced configuration clashes between multiple parties, we would really like to hear from you, because we're continuing this work, and we want to sort of discover the various ways in which different parties can disagree and how they actually resolve those disagreements. Okay, we're going to be around in Slack. Kevin's around in Slack as well. And I'm perfectly happy if you want to have a longer conversation to make a Zoom meeting time separately. All right, I'm going to stop here. I really want to leave time for questions.
Fantastic. Thank you for leaving us so much time for questions. Let's see. Do we have any hands or comments in Slack? Oh, we've got one hand from Peng Zhang. Go ahead, Peng.
Okay, thank you. Next talk. Okay, my question is, you talk about the background is two teams will need to synthesize a single program, maybe running on infrastructure. Well,
so clarification. Sorry about that. Synthesize a configuration.
Yeah, sorry. Synthesize a configuration. And how, I'm not sure how often does that happen in real cases? For example, in some providers or large companies, how does that often, is that often the case that multiple teams will handle the same infrastructure?
So I think the answer is a little subtle, right? The synthesis technology that we've seen so far in the academic community, by and large, focuses on these monolithic configuration settings, right? You're in a data center and you're trying to synthesize configurations for that data center, or you have an enterprise network and you're trying to synthesize configurations for that. The thing that we came across when we started just sort of naively trying to apply synthesis technology in the microservice architecture domain is that in this particular setting, we were coming across situations where, okay, the provider has a configuration, and then the customer also has a configuration, right? The provider might be configuring Kubernetes, and then the customer is trying to configure Istio, right? And in these situations, which in our discussions with providers are fairly common, we need synthesis technology, or we could use synthesis technology, not just to come up with the configurations, but to resolve the conflicts that inevitably arise, right? The pitch of this work is not so much yet another synthesis application as maybe a call to arms to look at the unsatisfiable case, the case when there's a conflict and synthesis doesn't just work out of the box, and see what we can do then.
Okay, thank you.
Our next question is from Aditi.
Hi, Tim. Nice talk. So I just had a question in the sense of that you mentioned that, like, if, let's say, the goals are unsatisfiable, you will take a goal and we'll try to see, like, what should, for example, B do to satisfy A's goals. But I was curious in the sense, how do you choose the goals to be satisfied? Like, the reason the goals were, let's say, not satisfiable, it means that, like, the whole set of goals can together not be satisfied. But then, like, do you really prioritize, like, okay, team A has more important goals and we'll try to satisfy those first? So, like, yeah, that's the question.
Let me answer your question also in two parts. So first, I'm making a bit of a radical assumption here in this presentation, right? I'm assuming that companies have exhaustive sets of intent at all, right? That's not necessarily a realistic assumption. And so some of our ongoing work is looking at how we can communicate useful information in the case of conflicts, even when the goals are not exhaustive, right? So for instance, in a configuration change setting, right? But more to your point, I think this idea of prioritization, this may be a way that you might start thinking about resolving the conflict, right? If your settings are more important, if your goals are more important than mine, sorry, there's a fire truck going by. If your settings are more important than mine, if your goals are more important than mine, then maybe the negotiation is weighted a little bit more in your favor. And in our paper, we have two different interaction frameworks one for this sort of weighted differently situation, and another where the administrators are a bit more equal. But I think it's true that knowing what you can do to get me my goals adds some color and dimension to that negotiation beyond just saying, here is what I need, here's what I need, here's what I need. Did I actually answer your question? I'm not sure I did.
Oh, maybe I need to give her permission to unmute. Oh, she remuted herself. Okay. I don't know. Maybe she has fire trucks in the background too.
Yeah, I'm back. Yeah. So that does answer the question. Thank you.
Good.
Perfect. Well, thank you so much. And thank you to all the presenters in this session. We've had a lot of really interesting talks. And so in order to maximize the HotNets experience, we're going to jump into some breakouts now and talk about all of the papers. Tom, do you want to kick us off into breakouts?
Right, let's get started. So welcome to a wireless session. The first speaker for the session is going to be Min-Sung Kim, who is a PhD student at Princeton. His interests include 5G wireless networks and quantum computing. So he will talk about how to combine both in one system. So Min-Sung, whenever you're ready.
Thank you. Thank you for the introduction. Hello, I'm Min-Sung Kim from Princeton University. Today I'm going to talk about hybrid classical quantum computation structures in wireless systems. There exist many performance goals in 5G or 6G wireless networks, and these levels of performance will enable many new services and thus much better user experiences. To achieve these goals, significant progress has been made in designing new wireless technologies, and integration and combination of these technologies are very promising to achieve the goals. However, these advanced wireless technologies entail computationally heavy processing, including various optimization problems. In general, for these technologies' optimal performance, the amount of computation is increasing exponentially for higher throughput. On current wireless systems, they still remain impractical because of the limited processing time available. So the computational capacity on the system becomes a bottleneck for next levels of wireless performance. And this is a serious problem since even future conventional computing resources will likely not suffice. They cannot achieve Moore's rule anymore, and their clock speed has already reached the plateau. So there is a new approach, the use of quantum computation for wireless systems. Quantum computation is a fundamentally different type of computation that has a potential to overcome these limitations. This approach assumes that quantum computers will be co-located at the centralized data center, and they will solve heavy processing that bottlenecks higher throughput wireless systems. And this centralized structure is a fairly reasonable assumption since apart from quantum, centralized radio access network, also known as CRAN, is a very promising architecture of future wireless system for many practical reasons. In this regard, this work focuses on the use of quantum and classical computation together. We want to explore the feasibility of hybrid computational structures where both types of computation are used instead of only quantum computation. Since each computation resources has its own pros and cons, so if we utilize them together properly, hybrid design can likely bring some benefits by taking advantage of both types of computation. For this paradigm, we design a prototype in order to see if hybrid design can achieve better performance compared against fully quantum design. Before we talk about hybrid design, let's look at how we can utilize quantum computation as a primer. These are very simplified steps for it. So we have a problem of interest. Then we need to transform the problem into a form amenable to quantum solvers, which are known as QUBO, or more precisely, equivalent Ising form. And this is the QUBO form. It's basically a minimization form whose objective function consists of linear and quadratic terms with binary variables. And the value of objective function is called QUBO energy. And this is an example. In this example, bit string or state 1, is the answer of the QUBO, which is the ground state whose corresponding QUBO energy is global minimum. And quantum solver is a heuristic QUBO solver. It accepts this QUBO information as an input and outputs a state per sampling. And at the end, it filters the best state with the lowest QUBO energy among all sample states as a final solution, which means the goal of the solver is to sample the ground state at least once among all samples. For quantum solver in our prototype, we make use of quantum annealer, which uses quantum annealing algorithm to solve cuboform. So initially, quantum annealer prepares a quantum state where it holds every possible state. Then it applies quantum annealing, which is an algorithm that turns this quantum state into a classical state. Here, the algorithms depend on how to control scheduling parameter S from a fully quantum state to a fully classical state. Now let's move on to hybrid design. These are three fundamental hybrid computational structures. Classical computing can be used for pre-processing of quantum computing, or the other way around, or they can process in parallel. And all combinations are also possible. However, choosing the partitioning scheme itself, which one does what, is an open question and one of the most important design challenges. In our prototype, we make use of reverse annealing, whose computing method naturally provides an opportunity of hybridization. But let's first take a look at how forward annealing works, which is the baseline fully quantum algorithm in this work. Here, x-axis is computation time, and y-axis is annealing schedule with parameter s. And forward annealing starts its computation from a fully quantum state, and it goes forward to a fully classical state as we saw before, except that we introduce anneal pausing in the middle, since it has been shown that introducing pausing can result in better performance. In the case of reverse annealing, which is a part of our prototype, it starts its computation from a programmable classical initial state. And this part is an opportunity of hybridization. From a given classical state, it goes back to quantum state and introduce pausing for the same reason, and then goes forward to a final classical state. So it's doing some refined local search from a given initial state. So for this algorithm, we need to decide this initial classical state. In our prototype, we make use of greedy search, one of the simplest classical solvers. The solution of greedy search is often not the ground state, but this can be a good initial guess. And by choosing the simplest solver, we ignored most of the complex design consideration. And this simple design makes it easier for us to do a direct performance comparison against the pure quantum solver. So this is a summary of our design. So our prototype is consisting of greedy search and reverse annealing. And initially, greedy search solves the QUBO, and quantum solver or quantum annealer applies reverse annealing based on greedy search solution. So it's sequential classical quantum hybrid design, where classical computation does pre-processing for quantum computation, which corresponds to this one. To test our prototype, we pick large MIMO processing as an application whose quantum annealing baseline performance is provided in previous work. Now let's see the results. Let's first talk about evaluation metric. TTS, or time to solution, is our evaluation metric, which represents required compute time for heuristic solver to obtain the ground state with target confidence. The first step to obtain TTS is to set a target success probability. Then we need to obtain the required number of samples to achieve that target success probability. And what is success probability here? Considering the goal of the solver, success probability can be defined like this. And here, this part is each sample's success probability, which means this orange part is a solver's failure probability, where all samples fail to find the ground state. So 1 minus solver's failure probability is the solver's success probability. Now, if you replace this success probability with our target success probability, we can obtain the corresponding required number of samples using the same equation. The last step is translate the required number of samples into processing time by considering each sample duration. Here, these two are main factors that decide TTS value. In our tested algorithm, their sampling durations are pretty similar. So each sample's success probability, the upper one, is directly related to TTS performance. So let's compare this probability for different algorithms. There is no theoretical way to get this probability, so we empirically obtain this by testing 200,000 samples for each algorithm. And this is the result of 18 by 18 MIMO detection with QPSK modulation for 3 different algorithms. Here, fully quantum corresponds to forward annealing we discussed before, which is a baseline. And this one is our prototype design, consisting of research and reverse annealing. And we also tested reverse annealing initialized by randomly picked state, and we call it naive reverse annealing. As you can see here, our prototype design obtained the highest probability. Since this probability can also represent sampling quality, so we can say that improved sampling quality is achieved in our prototype compared to fully quantum solver. Also, we can say that the gain achieved at our prototype is actually from classical quantum hybrid design, not just from reverse annealing itself, since we have shown that naive reverse annealing obtains a lower probability than fully quantum solver here.
2 minutes.
Okay. Now let's compare processing time. This is the relationship between each sample success probability and compute time for 3 different target success probability. And these are corresponding points of each algorithm. If we focus on target success probability 990%, which is commonly used value for TTS comparison, we can see that required processing time is only 4 microseconds in the case of our prototype, while fully quantum solver requires 20 microseconds. So speed up is achieved, and similar results can be obtained for different MIMO size and different modulations. In conclusion, we outlined a vision of hybrid classical quantum computational structures and explored the feasibility. For this, we designed and implement a hybrid prototype based on reverse annealing. And even with the simplest classical solver, our prototype was able to achieve speed up over pure quantum solver. And this is the first application of reverse annealing in wireless system. Most of discussion in this work are related to near-term quantum computers and near-term quantum algorithms for optimization, such as quantum annealing or QAOA. And current quantum computers are not immediately available for practical use for many, many reasons. However, we believe similar potential benefits of the hybrid approach could apply to future advanced quantum computers and algorithms as well. So the speed up we observe in this work is a very promising indication to the advanced state of the art. More detailed results and discussions are available in our paper. Thank you.
Thank you. Now we have time for questions. Let's see.
Can I ask a question? I can't raise my hand. This is Heather.
Oh, yeah, go ahead. Just ask that.
Oh, thank you for that. Was oh gosh. So I was just wondering, by making this initial state selection very helpful, are you making a suggestion that having more domain knowledge about the problem you want to solve is going to significantly help the ultimate solver? And what if you guess wrong? Is there any way to stop any wrong decision to affect everything else? I think we can't hear you. You're mute.
You're muted.
Can you hear me? Can you hear me now?
Yes.
Yeah, so we use greedy search as an initial solver, and this is the simplest solver, so its solution is often not the ground state, which is optimal solution. So many cases, the initial state is wrong, but reverse annealing does some refined local search from a given initial state. So it's doing so somehow we can say this is kind of error correction from the initial state. Does this answer your question? Can hear you.
And then we can discuss this offline. I think there's
okay.
Okay, thank you. I think we also have another question from Akshay.
Hey, hi, Minsun. This is Akshay from Carnegie Mellon. Amazing talk. So I wanted to probe deeper into the baseline that you use. So there are a lot of classical algorithms that have tried to optimize this 18x18 MIMO using, maybe instead of using one matrix, they have tried to divide it into two matrix and try to do a lot of other cool things to significantly speed up the process. So my question is of two parts. First, how close in terms of latency and obviously processing power quantum would be always better, but how close in terms of latency are these quantum hybrid solutions closer to the classical solutions? And secondly, at what point of time in future do you envision like this kind of solutions will overcome the classical solutions?
First of all, so in previous work published in SIGCOMM 19, they already showed the quantum solver for MIMO detection can achieve speed up. So in the case of 18x18 MIMO detection with QPSK modulation, so it takes only like less than tens of microseconds. And this is much faster than classical solver because the original form of optimization is maximum likelihood detection, which is the optimal one in MIMO detection. And if we want to solve optimal detection using classical solver, then you need to use sphere decoder or sphere decoder, which takes a lot of time to solve the equation. So I believe at least there is like 10 times faster speed up from classical solver.
Yeah, but I think there is there's a disconnect. I am talking about heuristic solvers that try to do it fast.
Okay.
You know, that primarily focus on latency, even if some channels are not correctly aligned, that's all right.
So you're talking about the heuristic classical solver.
Yeah, exactly.
So in literature, it has been shown that quantum annealing can achieve speed up compared to the best classical heuristic solver, such as simulated annealing. So actually, so this work focused on speed up of hybrid design over pure quantum. So we didn't care about classical heuristic solver, but in principle and in theory, it has been shown that the quantum computation can achieve speed up over classical one.
Okay, thanks for the answer. Great work.
Okay, thank you. So let's take the remaining questions offline.
Okay.
Next up, sorry.
Sir?
Yeah.
Can I start my screen sharing?
Yes, please.
Okay.
Yeah, so next up, we'll have Vibhav Singh from CMU. His interests are broadly in wireless and sensing systems. So he'll tell us about full duplex. Vibhav, whenever you're ready.
Thanks for the introduction. Hi, I'm Vaibhav, a PhD student from Carnegie Mellon University. And today I'll be talking about our paper, Full Duplex Radios, Are We There? This is a joint work in collaboration with fellow PhD student Akshay Gadre and Professor Swaran Kumar. So when 5G was initially discussed, full duplex was deemed to be an important component of the plan because of the immense gains it offered. However, we find today that it hasn't taken off as much as some of the other components, and we'll try to find out why. Before we begin, let us try to find out what makes it so exciting. With the help of a simple example of our daily conversation where when one person talks, the other person generally listens. This is similar to half duplex communication. On the other hand, in full duplex communication and sometimes presidential debates, both the parties try to talk at the same time, and if appropriate provisions are not in place, it would only lead to chaos. In a more formal setting, full duplex communication allows us to transmit and receive at the same time in the same frequency band. And this gives us around 2 times improvement in throughput compared to other half duplex regimes. This is what makes it exciting. There's been a huge body of work in academia on full duplex techniques over the past decade. However, in industry, we do not find as much traction in terms of deployment in end user devices like cell phones. So in today's talk, I'll not be presenting a novel full duplex technique, but instead, I'll be presenting our perspective on what is preventing full duplex from being deployed in Wi-Fi and cellular end user devices. In answering this question, we find that the problem does not lie at the physical layer where a lot of work has been done, but instead at the layers above and below it of network and hardware. The remainder of this talk will be focused on explaining the problem at these two layers. That is, at the hardware layer, IC implementations of full duplex circuits remain power and space hungry. And at the network layer, asymmetric traffic patterns reduce the gain of full duplex. I'll end this talk by commenting on some of the future directions for full duplex research and also provide some applications where full duplex techniques are useful today. Let us begin at the hardware layer. To understand what makes full duplex circuits power and space hungry, we'll first need to understand the basic working of a full duplex transceiver. Because it has to transmit and receive at the same time and frequency, it suffers from the problem of self-interference, which is the transmitter's own signal leaking into its receiver. This self-interference signal is almost 100 times stronger compared to the designed signal and needs to be cancelled. Because we have to cancel such a huge amount of power, relying on DSP techniques alone will not be sufficient. One has to divide this task among the antenna, analog, and digital sections of the chain to achieve this high power cancellation. In the context of a small end user device like cell phone, antenna and analog cancellation is generally implemented on a compact IC, and digital cancellation is implemented on a DSP chip. The challenge that lies here is to achieve the required cancellation while remaining within the power and space constraints of this device. So let us now begin our journey with the first layer of antenna cancellation, where generally a circulator is used. A circulator is a 3-port non-reciprocal device, which essentially means that it allows input signal to go from one port to the adjacent port only in one direction. It does not allow the signal to flow in the other direction. And this fits in perfectly well in the context of our full duplex transceiver, where we need to prevent the self-interference from leaking into the receiver. Now that we have understood how a circulator works, let us dig deeper and find out how it's implemented on a circuit. It generally uses two bulky permanent magnets, which redirect the input signal to the adjacent port using a magnetic field. It is obvious that implementing this on an IC is infeasible because of the bulkiness of these magnets. So recently, there have been some designs of active circulators in the IC community where these bulky magnets are not used. However, they remain too power consuming. As the name suggests, they are active. Moving on to the second stage of analog cancellation, generally a cancellation chip is used to estimate the self-interference channel and remove the residual self-interference. An important thing to note here is that to achieve a sufficient degree of cancellation, one has to estimate a large number of channel taps to accurately account for the multipath effects. Now that we have understood how this canceller works, let us zoom in to find out how this cancellation block is actually implemented on a circuit. We find that there are two approaches. In the first approach, time domain delay lines are used to implement the phase of the channel taps. And in the second approach, frequency domain filters are used to implement the frequency domain channel taps of the self-interference channel. However, there are still some problems with both these approaches. The time domain approach requires huge length of cable to implement even a small amount of delay. And the frequency domain approach remains power hungry because of the components it uses to implement these filters. So these are the reasons why full duplex circuits at the antenna and analog level remain either too power intensive or require a lot of space. Now that we have understood the hardware aspects, let me put you in the shoes of a hardware designer of a cell phone company and ask you this question. Which one would you choose, a full duplex radio or a 2x2 MIMO radio to achieve similar throughputs, but you have to expend the least amount of power? At first blush, it would appear that a 2x2 MIMO would require more power because it uses more number of streams. However, when we ran our analysis to compare the power consumption of full duplex ICs against MIMO ICs using similar technology, we found that full duplex consumes almost 57% more power compared to a MIMO IC delivering the same throughput. Another question that arises is, can we combine MIMO and full duplex to get multifold gains, perhaps by expending a little more power? To answer this, we extended our analysis, and here we plot the power consumption of full duplex MIMO hybrid ICs against half duplex MIMO ICs delivering the same throughput. We see that full duplex MIMO hybrids show a quadratically increasing trend in power compared to the linearly increasing trend in power of MIMO ICs, half duplex ICs. To explain this quadratically increasing trend, we need to look deeper into how these circuits are implemented. We see that it requires linearly increasing number of circulators and quadratically increasing number of canceller blocks. This quadratic increasing number of cancellation blocks is the reason behind this quadratic increase in power and space. This brings us back to the question whether full duplex MIMO hybrids is the right way to go, especially given that there are other alternate approaches which give the same gains, but at lower costs. Let us now move upwards to the network layer, where we find that full duplex does not yield the promised 2 times increase in throughput in reality. The 2 times improvement in throughput was based on the premise that both uplink and downlink traffic would be similar. However, in reality, we find that network traffic is highly asymmetric and skewed heavily in favor of downlink. Another observation is that as we move towards newer generation of wireless technologies, that is from 2G to 3G and 3G to 4G, this asymmetry worsens, or in other words, the uplink share becomes low. For this reason, full duplex can effectively deliver only 1.25 times increase in throughput instead of the promised 2 times. Another thing to notice is the performance of the 2x2 MIMO circuit, which is denoted by the red curve. It can be seen that it is unaffected by this traffic asymmetry. And these are perhaps the reasons why we see MIMO deployed in our phones today, but not full duplex. Despite the shortcomings of full duplex, we are hopeful that some of these challenges can be solved in the future with advances in technology. As I speak, there are ongoing attempts at designing more energy and space efficient circuits for self-interference cancellation at the hardware layer. And at the network layer, there have been proposals to deploy full duplex in more symmetric traffic scenarios like augmented and virtual reality. On the bright side, today full duplex techniques are essential for the operation of radar sensing and backscatter technologies. What makes them useful is that the cancellation requirements for these technologies are not that stringent. They generally require cancellation of a narrow band or a single tone. There are other places like base stations, access points, and backhaul relays where full duplex devices can be deployed because they have much less stringent space and power constraints. However, coming back to the promise of delivering 2x throughput to my phone from an access point, we believe that full duplex is not quite there yet. To summarize, we find that full duplex is not widely deployed today because of high energy and space requirements at this hardware layer and reduced gains due to traffic asymmetry at the network layer. We believe that some of these challenges can be solved in the future with more energy efficient IC designs and full duplex friendly application deployment. We also note that full duplex techniques are highly useful in radar sensing and backscatter technologies today. Thank you, and I'm happy to take any questions.
Thank you. So let's open the floor for questions.
You have a question from Tinjun.
Hi, this is Tinjin from Yale University. Very interesting talk. I have a few questions about regarding the recent advances in the IC layers. So, for example, I think the numbers you cite in your paper are not that up to date. For example, in recent past 2-3 years, there have been work on designing both circulators on chips, time domain, frequency domain cancellers on chip that actually consumes DC power that is up to 1 to 2 orders of magnitude lower than what was reported in the paper. So I was wondering, like, if you plug in those real state-of-the-art numbers from the papers into analysis, how would your claim still hold, and would you expect full duplex to perform really based on the state-of-the-art numbers reported in the past 2-3 years? And I think my second question is about your complexity that grows quadratically with respect to 2x2 MIMO. I think even the 2014 NSDI paper was saying that you can somehow share the delay lines between the elements, right? So even in that design, the number of circuitry needed for canceling the n-square path essentially only grows in order that is linear with vector n, right? So even that design was actually not using n-square many circuitry to cancel the n by n MIMO case. So I was wondering, like, how do you think about that will actually move forward, and how this full duplex will scale in even larger systems, not only for MIMO systems but also for phased arrays?
Yep. So thanks for the question. Coming to your first question, I understand your perspective, and as we mentioned in our paper and also in this talk, that there are already work being going on in the hardware layer to design more energy efficient circuits, and this is one of the good parts of full duplex, that in future we can expect them to be deployed in our devices. Why we chose the numbers that we chose was because there were two reasons. First, we wanted a more end-to-end performance evaluation of the ICs that we choose. And the papers that we chose for citing the numbers had already shown them not only in the circuits community, but also in the systems community like Mobicom. And coming to the numbers that you mentioned, why we are skeptic about those are because we have mentioned in our paper, but not in the talk, that enabling these ICs also requires some peripheral circuitry, and mostly those are ignored while reporting those numbers. So that is why we decided to not go with those numbers. However, as you mentioned, there's already work being done and going on, which will change the calculus and reduce the consumption of power in terms of full duplex. However, qualitatively looking at the message that we should take away from here is that how the complexity and power consumption scales, and vis-a-vis alternate approaches which can yield similar gains. Coming back to your second question in terms of enabling full duplex on MIMO, we are aware of the 2014 paper which showed MIMO full duplex capability, and it relied on using correlated channels. And we have also mentioned in our paper that we are aware of this, but why we stepped away from not presenting those results here is because things change when you go from a PCB design to an IC design, where you are much more constrained, and how the self-interference channel would change, whether it will be more powerful or not. These are aspects that were not clear how they would translate from PCB platforms to IC designs. However, that is an interesting approach to reduce the complexity, and we have also acknowledged that in our paper.
Thank you. I think we have time for a quick question from Fatima.
Yes, hi Vaibhav. Thank you for the talk. And I had a question in regards to the novelty of the insights. Most of what is presented here, my understanding is that is already well known in the community. The energy consumption for high energy consumption costs for full duplex versus MIMO, and the space and traffic asymmetry that you're talking about for full duplex communication. That's all sort of well known in the community. I was wondering if you came up with any novel insights that were probably not presented in this talk that you could kindly share with us. Thank you.
Yeah, so thanks for the feedback. Yeah, so some of the insights are known, like the traffic asymmetry are known in the community. And we wanted to bring out some of the energy and space complexities, which might not necessarily be known to the networking community because those are hardware aspects. So those were a few things that we wanted to bring out. And also some interesting insights that I got while learning about these papers were, what are the future directions that we could take? For example, in the hardware community, there are early approaches for reducing the time domain complexity by using something without going into details. They are, instead of using transmission lines, you can use something called switched capacitors, which help improving the energy and space requirements in IC. So these are some of the insights which we found useful.
Thank you. So let's move on to the next talk. Thanks again, Vibhav. And let's take the other talk, the remaining questions offline. All right, so next up, we have Reza, who is a research scientist at MIT working on ocean IoT. So that gives you a hint as to what he's going to talk about next. So Reza, whenever you're ready.
Thank you so much, Wenjun. So hello, everyone, and thanks for watching this presentation. My name is Reza, and I'm a research scientist at MIT. Today, I will be telling you about our research on battery-free underwater GPS. This is a joint work with my colleagues, Saad, Ozvi, and Fadl. One of the most revolutionary technology of our time is GPS. It has opened up an enormous amount of applications ranging from navigation to location-based services, and it has really transformed our life. Unfortunately, GPS does not work underwater. And the reason it does not work underwater is that GPS uses radio signal, which do not propagate well in water. And in fact, today we have nothing like a global positioning system for underwater environment, and it's actually quite challenging to build one. Now, you may wonder why we want underwater GPS. There is actually a significant amount of interest to develop underwater GPS because of its huge potentials. For instance, it enables us to use robotics for ocean exploration. We can send them wherever we want, and they can find their way back and bring us the information we ask for. You can have robots that are roaming the seas and map the seas, because today, according to NOAA, more than 80% of the ocean remain unobserved and unexplored. Another application of battery-free underwater GPS is the understanding of the climate and weather. Today, it is notoriously difficult to predict weather or to understand climate because we don't have location-tagged information from the ocean. And any model that we need to build for understanding the ocean requires to get not just information like temperature or pressure, but also to know where that information is coming from. This underwater GPS can allow us to get location information and build much more sophisticated models to expand our understanding of climate change. Last but not least, we can use batteryless underwater GPS to better understand marine animals. With this technology, we can localize, track, and study fish, for instance, to better understand their life cycle and also support endangered species. This knowledge is very important to make aquaculture sustainable, which is the fastest growing food sector of our time. Unfortunately, existing technologies fall short to provide us with a persistent and scalable underwater GPS. To localize underwater, people use acoustic signal or sonar. And the way it works is, let's say you have a drone that you want to localize underwater. The drone sends out the sound wave, and a network of anchored sensors respond back to the drone immediately after detecting its sound. By measuring the time that it takes for this round-trip pass, it can estimate the distance using the simple equation that we all know, which is the distance is equals to the travel time multiplied by the speed of the sound in water. And the factor of 2 here accounts for the round trip distance. Knowing the distance from each of these anchored sensors, the drone can do trilateration and position itself. And this is great, except that there is one problem. The problem is acoustic signals, they're very power hungry. And if you put these sensors continuously generating acoustic signal, they're going to run out of energy very fast. And this is why underwater positioning remains one of the largest research problems for oceanographic researchers. Today, I will tell you about how we can build a battery-free underwater GPS. In this talk, I will first tell you how we have built and demonstrated the world's first battery-free underwater localization. And second, I want to tell you about the open problems and opportunities that can transform our early demonstration into a practical worldwide system that can impact all the areas that I told you. Now, let me tell you more about our idea and how we have developed battery-free underwater GPS. We propose to replace the sensors with the battery-free sensors. Now, when the underwater drone sends out the signal, the way these battery-free sensors work is they first harvest energy from the received signal. Then, after harvesting sufficient amount of energy, they start replying back to the drone. In this way, the sensor can completely operate battery-free. It is also low power, scalable, and very cost-efficient approach. And we can deploy large number of these battery-free anchors underwater and let them stay there forever, since we know that they will wake up once we need them. But clearly, there is an issue in this approach. And the problem is the wake-up lag. Because the sensor needs to first harvest energy from the signal, which is going to take some time before they wake up and respond back. And so this wake-up lag is going to create an additional time that's going to prevent you from being able to accurately localize. And indeed, the bigger problem is this wake-up lag is completely random and depends on how far the sensor is, how strong the signal is, and how the environment looks like, and so many other factors, which make it extremely hard to actually compensate it. So the key idea that we had to address this issue is inspired by our group's previous work, is to use backscatter sensor for localization. The way underwater backscatter work is that you have a transmitter and receiver. The transmitter sends the signal on the downlink. The backscatter sensor then harvests energy from the signal, wakes up, and starts responding back to the receiver by modulating the reflected signal. Using the backscatter, the sensor can communicate without having any battery, and we can potentially use it to realize battery-free underwater GPS. But how this is different, and why with this approach we can overcome the lag issue? Let me tell you why. Let us go back to when we send the signal on the downlink. This signal will be reflected back from the backscatter sensor, regardless of it is charged or not. The signal is not going to wait for the sensor to power up and then to reflect back. It's going to reflect back right away. And when the backscatter node gets charged, it will start actually modulating the reflected signal. So then, how we can measure time of arrival when we do have continuous reflection in backscatter? And the answer is phase, which has been well studied in wireless localization. The phase is equal to the 2 pi multiplied by the distance divided by the wavelength. So if we can measure the phase, then we will be able to extract the distance and use it to get the location. Now, the wireless people in the crowd might now say that if there is a wake-up lag, you will also get a phase shift. But the main difference here, however, is that there are really 2 different notions of time. One that corresponds to the reflection time, which is independent of when the sensor wakes up, and the second is when the sensor starts backscattering. Interestingly, the wake-up lag does not really impact your channel estimation, and because all you just use is as a code to isolate the reflection coming back from the backscatter node from all other reflection in the environment. So the basic idea here is that backscatter acts as a code, and phase of continuously reflected signal is not impacted by the wake-up lag. So what I described to you is a basic idea. For those of you familiar with this equation, you know that the phase will also wrap, and there exists an ambiguity here. To address this issue, we use multiple frequency to estimate the channel and to resolve this ambiguity. Now, I've tried to explain our work at a high level, and in our paper, we show how you can build on this idea and adapt frequency-based localization to enable accurate underwater positioning. And in fact, we ran an experiment in the Charlottesville in Boston. So let me show you our experiment. In this experiment, we place a battery-free sensor at 3 different distances from the transmitter, and we try to localize it. The x-axis is the distance, and y-axis is the signal amplitude, which its peak correspond to the estimated location. Those dashed lines are the ground truths for 3 locations. Now, for the first distance, this is what we get, in which its peaks correspond to the estimated distance. Similarly, for the second and third distances, we got these curves. These early results show that backscatter localization enables accuracy of about 10 centimeters in battery-free underwater positioning. Now, while this result is very exciting, what I want to also highlight is that there are so many open problems and challenges than what we already have here. And what I want to spend the rest of my talk telling you about is some of these challenges. So let me tell you about the one that we thought was very interesting and very different from what you typically expect. When you send a signal in underwater, the signal doesn't just travel on a straight path. It also reflects off the surface, and it also reflects off the bottom. And not only that, it also reflects back and forth, and so on and so forth. So while multipath is typically something that researchers know, the underwater environment is almost like a waveguide, and it's not just like multipath. So, for example, if you went to run an experiment in the deep water, we will not end up having so many reflections, and we can receive a clear signal. Here on x-axis, we have a time, and on y-axis, we have the received signal. The signal for deep water, you can see it here. You can see the signal is quite clear. The symbols are very clear. Lows are zeros and highs are 1, and we can decode this signal easily. However, when we move to shallow water, this is how the signal will look like. When instead of getting clean signal, you will get much more distorted signal. This distortion is typically referred to as intersymbol interference, which seems to be very severe in case of shallow water. Now, in our paper, we describe how by adapting to underwater environment, you can partially mitigate this problem, but still comprehensively answering this challenge and issue is an open problem. Now, another problem is how we can scale this system in terms of its range and networking. Our own prior work has demonstrated the feasibility of underwater backscatter and how we can communicate up to 60 meters. And here there are still many open problems. For example, what new localization problem arise at longer distances? Or can we build multi-hop backscatter architecture for longer range localization? And finally, I want to tell you about the problems and opportunities beyond localizations. So far, I've told you about how we can do one-dimensional localization. But what is even more important is for us to go to 3D and even go beyond localization so that we can enable robotic navigation in the sea, so that we can enable things like tracking fish and manipulation so that you can enable robots to, for instance, grasp objects in underwater. And all of these are very exciting because of their technical challenge. And there is so much potential in defining the future of how this technologies looks like. And we have only started scratching the surface. And because we believe in the potential and the challenge and want you to join us on our journey, we have already released our code and a schematic and a step-by-step tutorial for how you can build these sensors from scratch. Also, just last month, we ran a large NSF-sponsored virtual conference called Smart Ocean 2020 to bring together oceanographer and computer scientists on a common platform to blue sky the future of ocean. The conference was so successful that NSF might start a new program focused on ocean IoT with up to 80 million investment in this area, bringing together computer scientists and oceanographers to accelerate this field forward. And with this, I want to thank you very much for listening to this talk. Today, I had this pleasure of telling you about our work and the vision for battery-free underwater GPS. We are very excited about this project, and we look forward to your question and to you joining us on our mission as we try to explore ocean worlds, understand climate, and support food security. Thank you.
Thank you. So we have time for questions.
I can ask one question. So, Raza, can you elaborate more on the challenges from the underwater channel? For example, how is it affected by the depth variation or by currents in the water itself?
It's actually a good question. So as I mentioned, one of the biggest challenge in underwater environment is the multiple reflection that we have in that environment. So if you go to shallow water, you will have a lot of reflection, and what you will get is a lot of intersymbol interference, which prevent you to actually decode the signal. So that's one challenge. So basically, you need to be aware of the environment you are, and you need to continuously adapt your localization scheme to your environment. That's actually a big challenge for us, and we have tried to address this partially in our paper, but still a more comprehensive approach as needed. In terms of those streams, basically because we are working with the acoustic wave streams, if they are like a common stream, they won't have big of effect when you are underwater. So they do have a lot of effect when you are working at the interface of air or water, but if you are in the water, we won't have a big effect of those streams and the signal that we will receive.
This is Heather. I can't raise my hand. Can I ask a question? Hi, thank you. That was very exciting. So if for a researcher to work on this, how do they do the evaluation? How is there any upcoming test bed or some kind of a simulator environment so folks can understand the challenge better?
Yes, so we have done most of our experiment for evaluation in the river. It's quite challenging, but it's also at the same time very exciting and very refreshing. But in terms of understanding the theoretical and the fundamental part of the problem, there are actually simulation toolbox out there. We have built our own simulation platform in MATLAB. It's not open source, but most of the tools are actually out there. So it's basically not that hard to build up on top of this work.
So I want to follow up on Heather's question. So ocean, or like not even ocean, but water body environment differs hugely, right? So how do you standardize some kind of event? So for example, I understand it's natural for you to do experiments in Charles River. Am I going to see something similar if I do it in the lake near my place, for example, or is it going to be similar to whoever who's on the coast somewhere else? So, and how do we think about this kind of comparison or different behavior and the like?
That's actually a great question. So as I mentioned, things here are a little bit depends on the environment. So if you want to do a great and a successful localization, you have to adapt to the environment that you are doing your testing. So for our case, we were working on a Charles River, which is not that deep. So it's basically, it was a challenging environment and it's considered as a shallow water. If you go to deeper water, things will get easier. But at the end of the day, this system will need to be tested in a multiparty environment to find a way that can adapt itself to all of them. We are actually planning to do a joint evaluation with our collaborators at Woods Holes that will help us to actually get to the deep water and try to test this system.
Thank you. Let's see. Okay. All right, so yeah, I guess so. I was also not just asking about localization per se, because that's even more environment dependent. But in some sense, Heather's question is, I would say, you can think of that question as more general in terms of if you want to do ocean. Basically, a lot of it is about the ocean channel, right? So, and that's what I meant by, it kind of depends on a different water body and stuff. So how do you basically build general ocean channel models, or at least a few example ocean channels?
Oh, basically the ocean channels, if you want to simulate the ocean channels, there are two main criteria. The first is how you are defining your water, the body of water, what is the depth? And the other criteria is what's the type of the seabed that you have for that environment. So the two main criteria to define the environment are these two criteria. And after defining this with your environment, then you can structure your experiment by defining where you have placed your transmitter or the nodes and where they have been placed, and then you can go ahead and analyze it.
I see. All right. Thank you. So we're almost out of time. So thanks again. Let's move on to the next paper, and then any other questions can be taken offline.
Thank you.
All right. So next up, we have Ali Abedi, who is currently a lecturer at the University of Waterloo And his interests are generally in the area of Wi-Fi sensing and low-power communications. He's on the market next year. So he'll tell us about how Wi-Fi is actually maybe more friendly than we have all thought about. Ali, whenever you are ready, please go ahead.
Can you hear me well now?
Yes.
Yeah, go ahead.
Thank you. Thanks for the introduction. My name is Ali Abedi. This is a joint work with Omid Abari. I'm going to talk about our paper, Wi-Fi Says Hi Back to Strangers. We are super excited about our findings, but before I present them, I have to review some of the basic concepts in Wi-Fi networks. A Wi-Fi network consists of an access point, like
Ali, sorry to interrupt, but you haven't shown your screen yet.
Oh, sorry. I assumed everything is fine. All right. Can you see the screen now?
Yes.
Yes, okay. Sorry about that. So a Wi-Fi network consists of an access point and a bunch of Wi-Fi devices, cell phones, laptops, right? How communication works here? Well, if the access point wants to send some data, it basically creates a packet and sends it wirelessly, for example, to the smartphone. When the smartphone receives the packet, it checks to see if the packet is healthy, all of the bits are correct. If that's the case, it generates an acknowledgement and sends it back to the access point to notify it that the packet was received correctly. If we have a private Wi-Fi network, which is protected by a password, such as WPA security protocol, we expect that all of the communications happen within this network because it's a private network. But specifically, if we have a device like the laptop on the right, we don't expect this device, which does not have the password for this network, to be able to communicate with the devices we have inside this network. However, to our surprise, we found something very strange. We found that if we transmit a fake Wi-Fi packet, and here by a fake packet, I mean it has no encryption, and the payload is garbage, all right? And the only valid field is the MAC address of the receiver. If we send such fake packet to a device, to our surprise, we found out that it sends back an acknowledgement. It looks like Wi-Fi devices don't care where these packets are coming from. And as long as they are correctly received, they send back an acknowledgement. For that reason, we call this polite Wi-Fi, because Wi-Fi devices respond to any stranger. So I tested this in the lab with a few devices, and by lab, I mean at home. But how many devices do I have? 5, 10? I'm not rich. So I thought, how can we basically design an experiment to make sure this is a widespread problem? So we thought, well, there are many Wi-Fi devices in the city, right? Everybody has multiple Wi-Fi devices at home. So why not we just move around the city and send these fake packets to these devices around us and see if they respond? So we designed this interesting experiment. We put a Wi-Fi card on my car, and we drove around the city, and I was sniffing the packets to see if devices that are around us, first of all, to discover the devices around us, and then we would send fake and we report if they send back an acknowledgement or not. Well, we continued this experiment for about 1 hour, sending fake packets and receiving acknowledgements. And I drove in low density residential and commercial areas in Waterloo for the duration of the experiment. Now, let me show you a list of devices that responded to our fake packets. Here's just a list of some of these manufacturers. Familiar names from Wi-Fi manufacturers, okay? And here, for legal reasons, I think I should say that you should not confuse this list with the sitcom sponsors, Okay, joking aside, during this 1 hour experiment, we found more than 5,000 Wi-Fi devices that responded to our fake packets. This is a widespread problem, but who cares? Is it important? In the paper, we have highlighted different threats and opportunities created by polite Wi-Fi. I'm going to review some of these threats quickly here. Okay, polite Wi-Fi creates all sorts of threats. Okay, let's look at some of them. For example, it can be used to figure out what you're typing on your phone or your tablet by analyzing the signal. I'm going to talk about this in the next slide. But before that, there are other threats, such as draining the battery of IoT devices. Wi-Fi, polite Wi-Fi can also couple with many Wi-Fi sensing techniques to create new threats. Techniques such as breathing rate and heart rate estimation and gesture recognition. Basically, polite Wi-Fi takes these existing systems and turns them into privacy attacks. Let's talk about keystroke inference as an example. Suppose that we have a victim device happily connected to its network, and then we have a bad guy, okay? This can be someone from outside the building. This guy sends fake Wi-Fi packets to this victim device, and it's polite enough to send back an acknowledgement. Now we can analyze the signal of these acknowledgement packets that we receive. Specifically, we measure the channel state information. If you're not familiar with CSI, you can think of it as some sort of very accurate signal strength indicator. There are studies that show that you can use CSI in this case to actually figure out what you're typing on the phone. But how is that possible? Well, your phone is sending signals out, right? And your hand and fingers move. So your hand will either block or reflect the signal. This causes some special patterns in the signal that's coming out of your phone, and someone can actually listen and monitor this signal to figure out what to type on your phone. You can also extend this to other Wi-Fi sensing techniques. Okay, this seems to be like sci-fi a little bit. Is this really possible or not? Well, we design an experiment where we have a victim device and an attacker in two separate rooms separated by a drywall. The attacker has no control over the victim device. Okay, totally random device. We send fake packets, we get the acknowledgements, we measure the CSI. Now, I'm going to show you how the CSI looks like in this experiment. The x-axis is time. The duration of the experiment was about 40 seconds. The y-axis is CSI amplitude. Again, consider this as a very accurate signal strength measure. At the beginning of this experiment, the target device, which is a tablet, was on the ground. So everything is stable around 25 dB. Then somebody approaches the device and picks it up. This causes sharp fluctuations in the signal. Then for about 10 seconds, we just hold the tablet. We see some slow changes. This is because of the small movements, probably. And then we start typing on the tablet. We can see that typing creates these special patterns. This is in line with previous work that showed that such patterns will emerge, and it's possible to infer what is being typed on the tablet. Then we put down the tablet and it stays there for a while. This simple experiment shows that polite Wi-Fi can be used to create all sorts of privacy threats. Remember, in this experiment, the attacker had absolutely no control over the target device. So he can be someone from outside the building sending these packets to the devices inside the building, and then he can analyze all of these signals to find out all sorts of information. Obviously, we are still at the beginning of this journey, and we have to look at all aspects of this problem. The second attack that I'm going to explain here is battery draining attack. Can we actually use polite Wi-Fi to drain the battery of battery-operated IoT devices? In this experiment, we use a low-power low-power Wi-Fi module commonly used in many IoT devices. It's ESP8266. So the idea is, if we send packets to it and force it to send acknowledgement, does that increase the power consumption? And how much is that? To find this out, we hook it up to a very accurate multimeter, and we measure the power consumption. In this plot, the x-axis is the number of packets we transmit to the Wi-Fi module, okay? And the y-axis is the power consumption of the Wi-Fi module in milliwatt. At the beginning of the experiment, we sent no packets to the Wi-Fi module.
2 minutes.
Thanks. In this case, because the Wi-Fi module is pretty idle at this time, it doesn't do much, it enters a power saving mode. It periodically shuts down its radio to save power, and it can do that. You can see the power consumption is pretty low, like something around 10 milliwatts. Now we start sending packets to the Wi-Fi module. We found that at around 10 packets per second, we can force the device out of the power saving mode, and it can stay on all the time. And this is a huge problem, because all of a sudden the power consumption goes up significantly to 240 milliwatts. And then we increase the number of packets we send to the device, and you can see that it linearly goes up. Makes sense, because it has to send more acts. At 900 packets per second, we have like 35x increase in power consumption compared to the base case in power saving mode. So Wi-Fi, polite Wi-Fi can enable different battery draining attacks. To conclude, now you know that Wi-Fi says hi back to strangers. This creates many new threats and opportunities. In this talk, I reviewed some of these threats, but there are many other things to explore. We are very excited about this project, and we would love to hear from experts in different areas to see what they think about polite Wi-Fi and its consequences. Thank you very much.
Thank you. We have time for questions.
Okay, thank you, Ali. I can ask a quick question. So can you comment more on how worried we should be? Like, should we worry more, or should we consider this as an opportunity or more as a threat?
I think we should be worried about this more as a threat, because in terms of consequences, we could come up with more threats than opportunities. And we are still gauging how dangerous this is. We are running experiments to see, like in real environments, when somebody has no control about like what's happening inside the building, and just by monitoring signal and doing this from outside the building, what type of information we can infer. But it seems to be a pretty nasty problem.
Interesting. I think we also have a question from Slack from Tom.
Sure.
So is there any limit to battery drainage attack? For example, how fast could someone discharge my phone using these fake frames?
Well, yes, we are basically physically limited to how many packets we can transmit per second, right? So there will be a limit. But the interesting thing is that in the paper, we showed that for example, for sensitive applications such as security cameras, for example, they run on batteries, and some of them claim that they run up to 1 year. The theoretical calculations that we had based on the experiment that we ran here showed that we should be able to drain the battery in a matter of hours.
This is Heather again. Can't raise hands. I have a question. I thought the behavioral sensing is very interesting as a tech, but without knowing what's really happening inside the building, how do you get ground truth and whether the pattern become consistent wherever the victim is at or holding the device?
A very good question, actually. This is all of the current Wi-Fi sensing techniques require training, right, and calibration. And in many cases, if you move to another environment, it breaks, right? Well, an attacker does not have the luxury of training in the target environment, obviously, right? So the question that we are actually targeting right now is that, can we find sensing techniques that are robust across environments? And there are already studies on this that show that it is possible to train models in some environments and then we apply it in another environment robustly. So this is actually one of the things that I am looking at currently.
Thanks, Ali. I think we also have another question on Slack. So are there any obvious mitigations? Like, can we choose not to respond to packets that do not come from an AP that if you're associated with it?
Good question. So I try to answer this quickly. This is a challenge, and we think it's not preventable probably. The reason is when a device receives a packet, it only has about 10 microseconds to respond. This is part of the standard. If you don't respond with an ACK within 10 microseconds, the transmitter assumes that the packet was lost and it will retransmit it. So it's crucial to respond very quickly. The problem is that right now when we receive a packet, we don't really have time because it's 10 microseconds and all we do is checking the CRC. So we can't do much. One of the things that we're looking at is, can we actually check the encryption to see if the packet was actually from one of the devices inside our network? From what I understand and the studies I have looked at, we need like several hundred microseconds to decode the packet in WPA2 standard, which is like an order of magnitude more than the time that we have. So until now, I believe that it's not preventable.
Okay, thank you. I think we can have one last question from Slack. Sure. So is this behavior standardized? And if so, the original motivation for the polite act should have some implication for the media access?
Sorry, can you repeat the question?
So is this behavior standardized? And if so, is the original motivation for the polite act, like does the original motivation for the polite act have any implication for the media access?
So basically, ACK, if I understand the question correctly, ACKs are mandatory in the 82.11 standard. And by default, if you receive a packet, for example, from your router, you must respond. This is part of the standard. You must respond with an acknowledgement within 10 microseconds. So if that's the question, that's a standard behavior. And that's why we believe that's a widespread problem, right? Because everybody is supposed to send an ACK and they don't have time to check if it's a valid packet or not. So the only thing they check is the CRC. Are the bits healthy? Yes, we don't look at anything else. Just send the acknowledgement quickly because we don't have time. I can tell you that out of all of the manufacturers that we tested, we did not find a brand that would not respond to fake packets.
And as a quick follow-up, was this like an OS specific issue, or like everything would actually, like all the different like iOS versus Android would actually reply to that?
Yeah, so we have seen this for like all different operating systems. Obviously, in the larger scale one, we couldn't know what type of operating system, but the controlled one that we we tested all sorts of devices, cell phones, tablets, routers, laptops. The problem is that the hardware is responsible for sending the ACK because it's such a short time. It's only 10 microseconds. So this mechanism is typically implemented in the hardware of your Wi-Fi card. It's in the firmware. So it's not like the packet arrives and then we pass it to operating system and figure out if you should send an ACK. There's no time for that. The hardware should immediately decide about the packet. So that's why it's hard-coded in the hardware. That's why I believe this is operating system independent.
Okay, we need to move on. Thank you so much again. There are lots more questions on site, so please interact more there. So the last talk for the session will be given by Mohammed Mazahari, who's currently a postdoc at the University of Waterloo working on millimeter wave. So Mohammed, whenever you're ready, go ahead, please.
All right. Thank you for your introduction. Do you have my screen?
Yes.
Okay. Hi, everyone. I'm Mohammad Mazahari, and I want to present my paper entitled Millimeter Wave Backscatter Toward Batteryless Wireless Networking at Gigabit Speeds. This is a joint work with my colleagues Alex Jain and Omid Abari. I am sure many of you have heard about millimeter wave. This is a new wireless technology that enables orders of magnitude higher throughputs. In fact, this is a technology that 5G relies on. Our community has also looked at using this technology for different applications such as virtual reality, Wi-Fi 1180, and data centers. It is an amazing technology in terms of throughput, but it consumes so much power and it is costly. On the other hand, we have the backscatter technology, which provides battery-free wireless networks. Examples of this technology are NFC, RFID, and Wi-Fi backscatter. They are great candidates for IoT devices because their power consumption is very low, but unfortunately their throughput is very low, just kilobit per second. In this talk, we ask how can we combine these two technologies and build millimeter wave backscatter, a network that has high throughput of millimeter wave technology, while it has low power consumption of backscatter technology. So let's first see what is millimeter wave technology and why it can enable very high throughputs. Millimeter wave refers to very high RF signals, very high frequency RF signals, and that's the benefit of them is that they benefit from the huge amount of bandwidth available. If you look at the RF frequency, here's what we are using for Wi-Fi, LTE, and so on. And here is millimeter wave bands. And you can see that they have a huge amount of bandwidth available. They can enable very high throughput networks. But unfortunately, this technology is fundamentally different from today's wireless technologies, and it changes the way wireless technologies work. So let me tell you the difference. Today, either if you use Wi-Fi or LTE, your access point uses omnidirectional antennas. So the device transmits the signal in every direction. No matter where you are, you can hear the signal. That changes with millimeter wave. In millimeter wave, systems use very directional antennas, and they cannot use omnidirectional antennas anymore. In fact, they have to use these antennas because their power decays very quickly with distance, and they need to focus their power to reach reasonable communication range. As a result of these directional antennas, the concept that I can just transmit and the receiver can hear doesn't exist anymore. So the communication is possible only after aligning the beams. In fact, if the devices move, they need to realign the beam again. And that changes the basic components of any communication system. Now, let's see how today's radio create these beams. Millimeter radios use phase arrays to create a beam. Basically, a phase array is a set of antenna arrays that each antenna is connected to a phase shifter. The phase shifter controls the phase of the signal going through the antenna, and the phase shifter itself is controlled by a digital controller and a software. So by having a phase array, we can create a beam and steer the beam electronically. Now that I said how millimeter wave works, let's see how backscatter technology works. In a typical backscatter system, we have a reader and a tag. The reader sends a continuous signal toward the tag, and the tag uses the signal to harvest energy and wake up. Then the tag either reflects the signal or absorbs the signal, and this signal is decoded at the reader, and this is exactly how the tag communicates its ID to the reader. Since the tag does not generate any RF signals, it doesn't consume any power, and it enables very low power communication. In the rest of this talk, I will present the tag. tag is essentially a millimeter wave backscatter communication technology that significantly has higher throughput than common backscatters, and also lower power consumption compared to other millimeter wave devices. In MMTag, we solve the beamforming problem of millimeter wave without using any active components and power-hungry components, and we only use passive components, so the power consumption is very low. And finally, I will present the implementation of MMTag and show how it can enable gigabit per second throughputs. Now, let me explain how MMTag works. Similar to any backscatter network, we have a reader and a tag. The reader sends a query signal to the tag, and the tag responds back. But because we use millimeter wave band, both the reader and the tag needs to create beams to be able to communicate. So how do we typically create a beam? The answer is phase array. Although I can use phase array at the reader, but I cannot use them for the tag. Phase arrays have very high power consumption, and they are not suitable for low power applications such as IoT. So the question here is that how can a tag generate and execute a beam without using a phase array? Our solution is passive beamforming. Let me explain our solution. Here I am showing you an antenna array. If we go ahead and write down the equations for the signal receiving to an antenna array from angle theta, here is what we get. Now, let's look at the equations when the antenna array transmits a signal toward the same angle. If we compare these two equations, we find out that the only difference is the sign of the phase shifts between the elements. This is very interesting. This tells us that by just inverting the phase of the signal, the received signal will be reflected back toward the same angle. So, how can we reverse the phase? Based on the analysis, we need a phase reversal circuit. What the circuit do is to receive the signal from the antenna element and revert the phase of the signals and feed them to the same antenna elements. As a result, the new signals reflect back toward the same angle. However, common phase reversal circuits employ mixers, local oscillators, and so other active components, so they consume so much power. So in MMTag, we employ the band-atta technique. In this technique, each antenna is connected to its mirror with transmission lines. In this manner, the order of the received signals is reverted, which results in reverted phase shifts. And as a result, the tag reflects back the signal toward the same angle without using any active components. Now that we have solved the beamforming problem, the question is that how can a directional tag modulate the reflected signal? To modulate the data, we use low power RF switches to turn the antenna on and off. Basically, what the switches do is to connect or disconnect the antenna from the ground. When the switches are off, the antennas are disconnected from the ground, so they resonate at 24 gigahertz, and they can receive their signal and reflect back the signal toward the same angle. But when the switches are on, the antennas are connected to the ground, so they don't resonate at 24 gigahertz anymore, and they can't reflect the signal toward the same angle. As a result, an OOK modulation is created by just connecting the data line to the control of the switches. Here's the MMTag prototype we have designed and implemented in the paper. In the figure, you can see the switches installed on top. Then this is the antenna. We have designed a six element array, each having two sub-arrays. And finally, you can see the feed networks that are set of transmission lines having equal phase shifts. Now that I have described the tag and its working principles, let's investigate its performance. First, we investigate the antenna performance. In this figure, we are showing the S11 versus frequency. The x-axis in this figure is showing the frequency in gigahertz, and the y-axis is the S11 in dB.
2 minutes.
Essentially, when the S11 is lower than minus 10 dB, we say that the antenna is tuned at that frequency. As you can see, when the switch is off, the S11 is much below minus 10 dB, showing that it is tuned well at that frequency range. In addition, we see that when the switch is on, the S11 becomes higher than minus 10 dB, it's around minus 5 dB, indicating that the antenna is no more tuned at 24 gigahertz anymore. As a result, the figure shows that the tag effectively modulates the signal. Next, we are going to evaluate the range and bitrate of tag. In this experiment, we place the tag at different distances with respect to the reader and measure the power of the reflected signal from the tag at the reader. Here, I'm going to show you the results. The x-axis is the distance of the tag from the reader, and the y-axis is the received power of the tag in dBm. Here's the results. As you can see, when the tag is far from the reader, the power of the signal is low, but still, it can enable tens of megabits per second. This is still much higher than other backscatter technologies enable. In fact, when the tag gets closer to the reader, the power gets even higher, and it can enable gigabit per second data rates. So to conclude, I presented the tag. tag is a backscatter technology operating at millimeter wave frequency. tag benefits from high throughput of millimeter wave technology while achieving low power consumption of backscatter network. Of course, we have just scratched the surface, and there are many other challenges which we need to address, such as interference cancellation, MAC protocol, and so on. But we believe that this technology enables many new applications in both communication as well as sensing domain. Thank you.
Thank you. We have some time for questions before we go to breakout rooms. So please go ahead.
We have a question from Fatima.
Yes, hi, thank you for the talk. So I have a question in regards to why we would need such high data rates for communication between the reader and the tag. So wave bands, I understand that it supports very high data rates, but why do we need it for this use case? Do you have any other use cases? Thank you.
Yeah, you're true. The data rate at millimeter wave is high enough, but the power consumption is too much that it provides them to be used in many devices. So far we have created a prototype that can communicate with the reader at low ranges because it is backscatter network, but it can provide at least 10 megabytes and at most and higher than 1 gigabit per second. But some use cases are for transferring data from memory, for example, a memory device that you want to transfer to read from this memory device at higher speed. This is not an application-based design, but I think it provides a good prototype. It's a good prototype for future applications, and I'm sure that in our community, many people need this high data rate, low power consumption prototype for many applications.
Thank you, Mohammed. I think I have another question. So can you comment on when going to higher frequencies like 60 gigahertz and having like a wide bandwidth of like 1 gigahertz, with such wide channels, what will be the challenges associated with that?
What kind of challenges? Sorry.
So what will be the challenges given now that you have such a wide channel? Like your channel is almost like 1 gigahertz.
Mm-hmm. So when you increase the frequency, your the path loss increases. This is because there's a natural way of electromagnetic communication. When you increase the frequency, you need to have very high, more gain to overcome this loss. On the other hand, your device becomes tiny. and you have to consider many other challenges in manufacturing because of their fabrication error and so on. But the main challenge, I think, is the path loss that's created for high frequency. But on the other hand, you have even much higher bandwidth, and you can even achieve much higher bit rates.
Thank you. And a quick follow-up question. So for example, if I want to go to much higher rates, how would I generate this like gigabit per second clock, given that it's like a battery-less system?
That's a good question. At digital's part, yeah, we should probably use very high frequency clocks, or using overclocking, or using the FPGA. That's another issue. Yeah, you're true. We need by increasing the bit rate, for sure, the power consumption of the digital section increases. But at the RF section, we are sure that the power consumption is low, not as low as this one.
Thank you. Yes, I think it will be like a nice trade-off to see which frequency to actually use.
Right. Yeah.
So I think we can either, oh, okay. Fatima, do you want to ask the question again, a follow-up question? We have time for one more question if you want.
Sure.
Okay, so yeah, so maybe I can rephrase my question. So between a tag and a reader, usually very low data rates are required. So it's very small amount of information that is mostly sent from the tag to the reader. So my question was that why would we need such high data rates between the reader and the tag?
Yeah, you're true. Yeah, you're true when you want to send, for example, just an ID.
Yes.
Right?
Yes.
It's an RFID that you want to send just a couple of bits for the reader. But if you look at other backscatter technology, for example, the ones that are used for Wi-Fi backscatter technologies, they want to transfer data rather than a simple ID, right? So if you have in Wi-Fi backscatter technologies, the common bit rates are about hundreds of kilobit per second, or sometimes you can achieve with some tricks megabit per second, but you cannot achieve gigabit per second. And that's the reason that we are traveling to millimeter wave bands, because we have a huge amount of bandwidth and we can communicate more data rather than ID.
Okay, thank you.
Thank you too.
All right, thank you. So we're ready for breakout. So let's continue discussions there. And also there are some more questions on Slack whilst the breakout rooms are being set up. Thanks again.